Give me a audio test on the podium.
1, 2, 3.
Welcome, everybody. Got a couple online too. So welcome to the second x86 microconference. Our reason for being here is if there's a RISC-V microconference, surely we can have an x86 one too. So here we are. Got a couple of great talks today. Just want to remind the presenters and everybody the main focus of today is to have discussions about things. So we want the presenters to try and get through their background and get to asking questions and having some nice lively discussion as soon as possible. So that's the main goal today. Yeah, if you want to ask a question in the room, raise your hand. We'll get the cube to you. Hold it very close when you speak into it. It doesn't seem to have very good distance listening to you. So hold it real close. Okay, first up today is David Kaplan. Let's go.
Oh, thank you. Well, good morning, everyone. And today I'm going to be talking about everyone's favorite subject, of course, which is speculative side channels and mitigations. And I am sure that probably everyone in this room would love it if these would just go away, and that we would not have to deal with these, and we could just delete bugs.c in general. But that's not the reality. And the other thing about the reality is that these things are actually very expensive. We were doing some internal testing on this recently with some recent AMD server hardware. You're looking at the cumulative effect of mitigations from the last 7 years, basically comparing the default out of the box settings, which have all the mitigations on, to mitigations equals off. And across a number of server workloads, the impact was something like 20% on average, right? And then there's some workloads where it was more than 50%. In other words, you pass mitigations equals off, your performance doubles on the workload. Like that's a huge amount of performance we have to worry about. So, I mean, you can look and say, well, hey, that's why we have mitigations equals off, right? Is the audio not working? Ah, we're working on that too. But unfortunately, we got stuff out there that somehow people still want to use. It's rather annoying. So, well, I'm not going to say that is AMD's strategy. But yeah, so we have mitigations equals off, right? But the problem is that this is a kernel command line parameter, and the challenge is that there's reasons why that is an awkward place to put this kind of policy, especially such an impactful policy. And so the proposal in a nutshell that I have here, calling dynamic mitigations, and essentially this just allows you to reconfigure the mitigation settings after boot. So it doesn't have to be in the kernel command line. It's a sysfs interface. You write bug-related, essentially command line options to this interface. Those can be bug-specific ones. It can be the new attack vector controls I talked about last year. It can be just mitigations equals off. And in response to this, the kernel will reevaluate the security settings and repatch itself. So that's essentially what it does. Now, I think the most interesting thing is why is this useful? And that's kind of what I want to mostly focus this discussion on. I can talk about how we're doing the repatching if that's of interest, but I think the first thing we got to get through is why are we doing this, and is this worth it? And there's 3 use cases that I've identified for this. If there may be others, and I'm certainly interested to hear from the group here if there are some. But the primary one, and the one that really motivated this work in the first place, is this idea of sort of late binding of policy and allowing the mitigation settings, which is basically a reflection of what the system is going to do and what the trust model is, to come later, like after user space is loaded. And a very common case where this is relevant is in a cloud deployment scenario. So my understanding is a very common deployment model is you ask the cloud for a VM. They give you basically an empty Linux VM. It boots up, it runs something like cloud init, fetches a configuration file over the network. The configuration file you wrote, and it basically says what you want that VM to be, how to configure, what to install, all this sort of thing. So that would be a great place to put your security policy of saying, do I need these mitigations or not? But right now, you can't do that because the kernel's already booted. It's already booted with the default settings, which are the slow ones. So even if you're only running your own code and you normally don't need these things, you're stuck with them. So with dynamic mitigations, this has an easy solution, right? Because you can boot up, you can read your config file, and then just write the sysfs file, you're good to go. So, in my mind, that's the use case that's going to see the most ROI, just because this is something that a lot of clouds are using out there today, and this is performance that's being left on the table. I do want to just briefly mention a couple other use cases though, and then I'll probably pause here and let everyone chime in. So the one is about mitigation changes. We have had circumstances where a specific mitigation has been found to be undesirable because it's been broken security-wise, or maybe it has bad performance characteristics. Many of the mitigations, there's 16 by the way right now, I think in bugs.c, have multiple mitigation options. There can be like 8 or 10 command line options. So, it's not unheard of for one of them to turn out to be not what you want. And with this interface, you can change those. You can respond very quickly to any kind of incident. No reboot required, right? That's definitely a big concern in the data center. And then, the final point here is one that probably, people like me get the most benefit out of, which is just that for mitigation testing, this is great. It is also useful because, as I say, many of these things do have multiple mitigation options that have different performance characteristics. And so you may want to run your workload and try out different ones and see what gives you the best performance. But additionally, with the dynamic mitigations, it's possible to come up with all kinds of combinations and quickly change these things. I mean, as part of my development here, I wrote some testing tools to come up with all kinds of crazy combinations of command line options here and look for whether the kernel does the right thing, and it found a number of bugs in upstream, and those patches have since been merged. But the point is that this is actually a way to get better testing on the code that we currently have in there. So as far as the patching itself, say it takes roughly 50 milliseconds. So it's not a super fast thing, but it's not a super slow thing either. You basically stop everything, you repatch. And so there is an RFC that's out on the list. The initial feedback on that was concerns about the complexity of this, and and I get that, and I want to have a discussion about that here, because mitigations are complex already, and alternatives and all that stuff. This is adding more into that, right? And my argument would be primarily the performance we're talking about here is so big that I think we should be considering a solution like this. But I would like to hear what the rest of the community feels like, and if they think this is the totally wrong direction. So we got a box, and I'm going to shut up.
I'll give you the hyperscaler perspective. Kind of boring because it's just like a thumbs up. We really hate rebooting machines. So the first thing about runtime policy, actually, I don't really care, but I can see it sounds like a good idea to me, but not important to Google. But the second thing, which is we constantly learning new things about mitigations. The thing that I think about the most is that we often learn about new exploits, and old mitigations fix those exploits. And we hate rebooting machines as a result of that, so we would love to do that without it. The thing that actually I don't think has ever happened, but which I think probably will one day, is that like some weird contortion happens in our workloads, which means that like Google search performance falls off a cliff, and the fix for it is to switch off the like SMT mitigation for specific. So there are cases where I'm like, yeah, let's just throw security out the window for a few days while we like keep Google search running. So like both directions make a lot of sense. So thumbs up from me. A conversation that comes to mind, which I'm a little bit hesitant to bring up, is that when we're talking about, oh, this old mitigation fixes that new bug, or new exploit, suddenly now I'm starting to think, I don't want to switch on the mitigation for the exploit. I want to switch on, in terms of, the configuration is in terms of like mitigate Spectre v2 or whatever, but instead I want it to be in terms of like do an IBPB on context switch. So I start to wonder if I actually really want mitigation, like per mitigation controls. I think it doesn't make sense to like throw those things together, but it might make sense to have the conversation together.
Yeah, so I will note one thing that I was able to do with this is, and this is in the patches, is I created a debug.fs interface to things like the x86 bug bits and things, so I could actually fake that CPUs were vulnerable to things they were not. Now, I didn't extend that to the point of being able to force feature bits, although that'd be a pretty natural extension because you could do that and then repatch, but that's really taking you into uncharted territory.
Yeah, but I mean, I don't know if you saw, I actually made a command line change that lets you set arbitrary feature bits. And that's the same thing where like you can obviously break the kernel horribly by doing that, but like people who are serious about fixing their CPU posture without rebooting probably have the time to think about it carefully. So I would be okay with having these like potential foot guns as long as it's documented as like, this is very, very dangerous. You better be a kernel developer if you flip this bit. But they're still useful bits to be able to flip.
Isn't that what debug.fs is?
Right, yeah, true. Yeah, so
I can't see any fundamental reason not to let people poke at those things for debugging purposes. They want to do debugging in their hyperscale cloud, that's fine. I mean, if you get a hold of pieces.
Any other feedback on this point? Or are we like, this is great?
Who hates it? Speak up now. Yeah, I mean, it seems like a good idea. I do like the testing seems like a real natural thing that, and it did. So, we gotta do.
My only problem is if some of those options get misused for something else. ID, set CPU ID, stuff like that. We've been trying to communicate that and say, okay, this is just no, you should not use that. And we have it like, I don't know, turn off a feature bit case, but as long as that doesn't happen, I guess we're fine. I guess we need to try to see first.
Well, then I'm going to try to go even a little bit more controversial, and because I want to have a discussion on this. I'll throw an idea out here and let people throw tomatoes at this. There are mitigations that we have upstream right now that are very complex, and they're very complex because they're trying to eke out every last bit of performance while still mitigating the security vulnerability. I mean, if you look at things like SafeRet, or maybe I'll pick on call depth tracking or something like those are very complex, and there are other mitigations for those same bugs that are simpler, but they're just not as performant. And I think it makes sense if we're going to be enabling mitigations by default for everyone to try to get the best performance that we can, especially on existing hardware. If we have dynamic mitigations, I wonder if we could get to a place where really only the users who need the mitigations are using them, and we could potentially fall back to more expensive but simpler mitigations for some things. We're not breaking anyone's security, right? But if the amount of people that are impacted by that particular vulnerability is very low, and everyone else is getting these things turned off, is that something that is that interesting?
It is a great thing because Linus is going to get the code simpler, so he's going to love it. We're going to remove all these.
Yeah, I mean, obviously the risk is that you can't really do that until people are turning these things off when they don't need it.
Andy has raised his hand.
Hi. Yes. So to a point earlier about having options and saying we hope people don't use these options for evil. The truth is that you present an option, and even if you say don't ever touch this, people will build on it. The documentation there saying this is liable to break your system, only do it if you're a developer, is kind of okay, but the moment it's put out there, people will use it.
Yeah, that's my fear.
Depend on it. So it's fine to do. You just have to be aware that the moment you do it, it's basically set in stone.
Are you specifically talking about command line options versus like a debug FS interface, or are you saying anything that we build?
You're hoping to build something that people will use, and you give them a way to use it, and they will use it in all the creative ways it can be used, even the ones you didn't want them to do. Which it's basically unavoidable, but you have to realize that that once you have put something in debug.fs and people start using it, you cannot control what people will do.
Yeah, but debug.fs is not for production. I mean, we don't care. Okay, go.
Linus told me specifically, if it's in debug.fs, it's still API. If someone finds a way to use it that creates a tool that's useful, and they use debug.fs, and then you move it and it breaks that tool, that will be reverted. So Linus has stated that, FYI. So debug.fs is not safe that people think it is.
Yeah, I guess I do just, part of the worry here is that these are kind of, break glass in case of fire kind of things. And we're only going to know whether it was a good idea, like once somebody has actually used it in practice. And it is all, I don't know, like you were saying, hey, if there's an existing mitigation that works for a new bug that shows up, it's so speculative. What?
Plenty of the recent bugs would have been mitigated by old mitigations. It's not like this isn't. I don't think it's fair to say it's speculative. Like I know VMscape, like there wasn't actually a bit you could flip, but the mitigation wasn't new. I think we should expect that new bugs have old.
And to be clear, I think you're also saying that there may be something that mitigates it. It may not be the best way to mitigate it, but if you need something on day zero.
Yeah, and if somebody wants to prove that, like, well, not prove it, but say, if we went back and looked at all the bugs and all the mitigations that we had and said, hey, at the time that this new thing showed up, we had these mitigations, and if we had this functionality in place for that bug, wouldn't have had to do X, Y, Z. Like if somebody wants to do retrospective, I would be motivated by that. I mean, because we can't look at the future, but we can look at the past and say, if we had this tool at our disposal in the past, we would have used it for X, Y, Z.
So basically, we're thinking about making that functionality more generic, not like mitigation, fix the specific mitigation blah, but enable IBBB, which fixes a bunch of mitigation.
I mean, we could. So as I say, the current patches create a read-write interface to the bugs vector. So, if there's a case where like you want to force some CPU to be vulnerable to some bug, or if there is, a mitigation that you kind of want to force. I mean, I guess one that potentially comes to mind is like the TSA issue that AMD had last year ended up basically using the same mitigation that MDS had. So maybe, as a hack, you could have forced the processor to look vulnerable and whatnot.
I mean,
say that one, it doesn't scare me as much because those are like actual vulnerabilities. Although there is still the fact that there's a set of Intel ones, there's a set of AMD ones, and there's a set of both. And like when I was doing my testing, I separated them out so that I didn't create some, weird processor that had, MDS and TSA or something like that. And so you quickly start to get outside of the design envelope when you expose these things.
So should we keep the debug.fs stuff out of tree for now until we're sure that even if somebody starts using it, we're going to be okay with it?
An option.
I think. Oh.
Go ahead.
Yeah, yeah, you were okay there, Peter.
Yeah, I mean, we have a much bigger problem with debug.fs, which is that it's an all or nothing thing. Anytime people start talking about debugfs being an ABI, I get, quite frankly, scared as heck, because it implies to me that we really, really need to start planning for factoring debugfs in a way that pretty much means that we're recreating sysfs. As it is, the whole the whole point with debugfs was a place where we can dump things that we're not entirely sure of.
Right, but on account of that, there are controls in it that are useful, and every production system will have debugfs there that you can get at in an emergency.
But okay, so one thing is, I think that's been actually a saving grace for a lot of things. I do know there's a lot of distros and what that do not mount debugfs, and if you have something that a application that depends on it being mounted, it just can't run on those systems. So there is that advantage. In fact, the whole reason why I created TraceFS was because people are saying we want the tracing facility without debugfs. So I created TraceFS for that.
Certain places that it isn't mounted, or maybe isn't even compiled in on the distro. But I think it would be reasonable in this case to say, like, if you want the flexibility to be able to turn these things on and off, that's one of the dependencies. I think that's okay here. Android disables it.
I mean, it would be okay if we made the policy that if there's something in debug, if exactly what Steve said about TraceFS, is that if we find something that we really want, then we're going to have to move it, and that tool is going to have to change at least the path name that it's using. That's a much more reasonable policy.
We've also kind of implied here the place that we care about this the most, I think, is the server space, because I think that's the most averse to reboots. Android, super important, but also, gets rebooted all the time and isn't a big deal. So I that sounds okay, not perfect, but okay to me.
Okay. Do you have another comment?
I just did a quick look at syskernel, and it used to be just syskernel. The only directory that was there was debug. And what happens if you enable the debugfs in the kernel? The sysfs directory will create a special directory called syskernel debug. Same thing for tracefs. If you enable it in the kernel, it'll be syskernel tracing. And that's one way to know if it's enabled or not. And now there's like 20 directories in syskernel. So this is now a method that a lot of people are doing. There's C group, crash something, FS caps, hard lock count, IRQ. I mean, all these are files or directories, but this kernel slab.
Comes to mind is, even if we keep this out of tree, and you guys, for instance, say, hey, we would want, let's just say we out of tree had the ability to flip on our mitigation bits, like
The debugfs part. Yeah.
if that was like IBPB on VM exit, right? If that was one of the bits that you could flip in debugfs, and you guys carried that, out of tree for a little bit, and you happen to use it, that would all of a sudden be a really strong reason just to merge it right away.
We already have out of tree stuff to do this, and we use it. So,
yeah. So similarly in Zen, we have the ability to turn all of those barriers on and off as we need to, and we have been asked by customers, hey, can I change this without rebooting? And the answer is yes. We use that as well.
Okay, so we got one big Linux user and Zen who are saying people will use it. That's a big proof point.
I'm a little bit confused about why you want to put it in debugfs. I mean, the obvious place would be we have the syskernel, sysdevices, CPU vulnerabilities or something like that. And having those, we have these SysFS files already which tell you whether it's vulnerable and what mitigations are there. So obviously extending those things to be writable, root only obviously, would be my intuitive choice instead of going through debugfs. I mean, you create an API anyway.
Yeah, that's an option. I mean, I had done it through debugfs because I thought this is really just for testing purposes, but apparently it's not.
I guess it's not.
Yeah, the one thing I'd worry about with the vulnerabilities files is how unstructured they are right now. Like the mitigation strings are kind of wonky and like, you know, it'll say vulnerable, but then it'll say mitigation, blah, blah, blah. And the mitigations are kind of wonky, but it's not, we can look at it at least. I mean,
Yeah,
it's a string in the end.
So I already went and fixed some of those, but it is not organized very well. There's like 5 things on the Spectre v2 string that, yeah, but we could definitely create a more structured way. I mean, to try to force at least the processor to be vulnerable to something. I mean, another thing is that those files do actually. It's not just are you affected, but also which mitigation it is, and that could get awkward because the mitigations also have cross dependencies.
It's worth saying there's also stuff in that CPU bugs file that's nothing to do with speculation, really. There's the ITLB multi-hit that went in there because it was done at the same time as a bunch of other stuff, but really is unrelated to everything else in there.
Yeah, most of the code there is related to speculation.
I'm going to bring another thing up that I'm a little bit embarrassed to open this kind of worms, but just to bear in mind, some of the out tree stuff we have is also not system-wide, but like I think we have a thing to like disable KPTI with a PRCTL or something like that. And I think some of them are actually in C group controls, which I guess is wrong. But like, yeah, bear that in mind as well. That so at one point we probably want to have this even finer grain control than system-wide. I guess you can't do that for every mitigation, but for some.
I will note that KPTI is like the one thing that I don't support toggling.
It's quite easy actually compared to. I think it's an easier case than what you've done.
I will note there's a couple other limitations here that are probably worth calling out just for the discussion, right? So one is eBPF. So like anything that you had JITted, when it gets JITted, you get some mitigations applied, and then after I repatch things, I don't know how to go and re-JIT it. I don't think there's an easy way to do that. Obviously, you could unload your programs, you could reconfigure, and then you could reload them. I also think that, in many of these cases, you're going from secure to potentially less secure, and so it's not a big deal if you had more secure mitigations applied. But if anyone knows some BPF magic or ways to better address that, please let me know. Or if anyone cares.
Microconf was yesterday or something, so wrong order.
We should have answered what I had the microphone. I just want to know. I don't really care about that. I do care, but like I wouldn't want. I think it would be crazy for that to block any of these other features, right? Like if I'm at Google, I'm like, oh, I want to update our mitigations. But I can't. I have to do this extra thing where I reload the BPF programs. I'm like, that's still way better than I have to reboot. So
yeah, no, that's fair. I guess just in the interest of going through both of my slides, I will just mention that this is the overall flow for doing the repatching. I'll just call out maybe a couple of highlights here. I mean, so first off, this is done under super duper big hammers, right? So everything goes into the freezer. There is a new flavor of stop machine I added called stop machine NMI that basically is stop machine but in an NMI context. So we don't even have to worry about those coming in. And then we go through and we basically revert the kernel text to the way it was when we booted. And then we go through and patch it just like we did when we booted. So the idea is to try to, minimize the state transitions that the kernel has to deal with just for complexity reasons. But it is a a long process. Yeah.
So why do you need this big hammer? I mean, there's basically almost nothing in there which has any going in, going out dependencies. It's just the barrier is there or not, or some other mitigation mechanism is invoked or not. So if you just patch it gradually, nothing happens.
So I need the big hammers for a few reasons. One is that first off, I can't have things running and use like the text poke BP stuff, because that's really only around like calls and the static call stuff, and it doesn't work for generic patching of alternatives. Additionally, I need to put
Then we fix rather the alternative stick patching to do that with a BP, rather than having this whole mechanism of get the big hammer out, do patching in NMI. I mean that really scares me.
Well, and another important thing while they're searching for another mic here is, we can't have tasks that are running the middle of a sequence that we're patching. And so that's one reason why we put them in the freezer, so they're not in the middle of like a call to a reptiline sequence or something that we're getting rid of. So this was, I know some case like this that Peter pointed out that, get very complex very quickly.
So I mean, if it's in the reptiline end, and you patch the call side to not call it,
that
doesn't matter
part's
because
fine.
you return.
That part's fine, yeah.
My question was actually to you. You mentioned that the text poke doesn't work generic. I mean, Kprobes uses it all over the kernel. So, I mean, what do you mean?
No, it's the alternative patching mechanism in x86 doesn't use it.
Yeah.
Can we make it use?
That's
Well,
what I suggested.
No,
But
Kprobes is just inserting and removing calls. That's quite simple. In the entry and the exit code, you've got hundreds of bytes of stub functions that you're either inserting or removing.
And you can be in the middle of them, because an alternative is not just one instruction. It can be a whole sequence. And that's another thing. If the task is in the middle of that sequence and you interrupt it.
So that's why you have the stop machine for him. Yeah.
Yeah. Okay. Fair enough.
The other thing to say is the text poke BP relies on taking a breakpoint, and the IREC from that goes and interferes with your NMI handling capabilities anyway. Fred will make this better, but there's currently no CPUs with it yet.
Yeah, I will say also the stop machine NMI, I use it for this. It's basically modeled after, I think, how Intel does microcode patch loading also, so it could potentially leverage that as well.
We should use the same one mechanism to do that. Split it out of microcode loading and make it generally available.
Overall, a comment from Thomas there is that he hates stop machine. He doesn't want anybody else using it. And if there is a way that we can generically do it, I mean, this is the kind of this is a lock Peter Z in a room and don't let him out until he figures a way to do it kind of problem. So maybe there's a better way to do it.
I mean, the purpose of this is for like mitigate. This is not something that's a common thing that people are going to do in normal daily. This is like emergency. I don't want to reboot the machine. I need to do something. So if you have some crazy stop machine, it's not. We're not going to be worrying about real time latencies. Yeah, that's what I'm saying. We're not worried about latencies or like that. Like stop. One of the things about stop machine is it's not even just real time. It just has a huge impact in the whole system. But we want the huge impact anyway. It's like we don't care. Better than the alternative of rebooting.
That was the logic. I mean, it's maybe something that could be optimized in the future as well. All right. Any other comments? I know we have a lot of discussion time, so. We don't have to use it all.
Yeah, I think your slot goes until 10:50. So if you have any more content, we could,
I do not.
okay. Or we can make an impromptu break time too, if there's nothing else to talk about. Or come up and chat with David after the talk if you want to. So, okay, well, this one early. The next one is in 15 minutes. Thank you, David.
Thank you.
Is it the same as last year, or it's just like
The same as last year.
It's very simple.
And I uploaded my slides to the website.
Yeah, they're there.
Second thing we have now. We have the program here. Doesn't have any slides. Let me ask Thomas.
Chang, are you on anywhere?
Yeah, I'm here. Hi,
Oh, here
Dave.
you are. I think we're still looking for Ahmed. So I'm thinking if we don't see him, we may throw you in an earlier slot if that's okay.
Yeah.
Just
Absolutely.
speculating.
Yeah. No problem. Yeah.
And Ahmed, you're not anywhere online, are you?
Yeah. I'll be around here. So.
Okay.
Be free. Yeah.
Just to let everybody know what we're going to do here. Looks like we're still waiting on our next presenter. If we don't see him in the next couple of minutes, we will take Chang's talk about APX and we'll move it on up. Oh. Okay, yeah, we're going to make a schedule change. Chang, if you're all in good shape, let's do yours early. Okay, and I think... So Chang, I'm going to make you the presenter. Do you want to double check that you can swap slides? There
Yes,
you
I
go.
can.
Okay.
Yeah.
Okay, Chang,
Okay.
you're up. Thanks for being flexible for us.
No problem. Hi, everyone. Let me present the new general purpose register available on x86. So the structure of this talk has two parts. First, introduction and background, and then second, discussion about the internal usages. As an introduction, let me try to summarize the spec documentation a little bit, and then closing with some compiler toolchain support. There's a feature called the Advanced Performance Extension. That feature introduced new 16 general purpose registers. And there are a few points to note. They are available 64-bit mode first. And the second, they are volatile registers in terms of calling convention. And then third, this new APX state is Xsave managed. The component is assigned as bit number 19. So, and currently the user support was merged earlier this year. And adding state component, I think is basically straightforward, but there's a unusual effect. That is a user exposition is through the Xsave non-compacted format. But its component number is after AMX though. Its offset is in non-compacted format is on the position where deprecated MPX state used to be. So it was managed by introducing a mapping table between component number to offset in non-compacted format. So that's the way it was a little bit smoothly merged to mainline currently. Now, in terms of enabling, there's a patch set floating around for the KVM support, but that's out of the scope today. Instead, the focus here is really about the in-kernel usage, which is kind of, I think, unique in a sense that the new general purpose registers are added after architecture introduction in the first place. And looking at other architecture, so far I think they are all once for all defined general purpose register. They may introduce a new one in the future though. For instance, ARM has 31 registers 2012 and RISC-V support for 32 registers in March 2017 and was defined in 2012. Other architectures like MIPS and Power look to have a 32 general purpose register already back 2008. So there is no precedent cases to reference for this regard. Now, let me briefly describe instruction encoding. Instruction is essential to access those resources. In a nutshell, instruction index doesn't really matter. So the idea is expanding the instruction bit width. APX introduced the new prefixes. Formerly in x86-4, there was a REX prefix. And there's a lower 4-bit that was used to address the 4th bit as a most significant bit. Now it is expanded to fully utilize upper 4-bit to expand 5th bit as most significant bit. And in this math, there is another bit that is actually indicated with the OP table, but that's not about the register index. Anyways, similarly, on the other prefix extension, like a extended VEX has a similar format. So that's I think, pretty much about the register expansion, but the feature looks to have additional sub-feature. There are a few examples I want to note here. The first is a new data destination. So formally, 2 operand was given, and the result was overwritten to one of those source registers. Now we have additional registers. It makes sense to separate them out, meaning the output is exclusively written to pointed destination register. Second case as a sub-feature, APX sub-feature, is related as push-pop instruction. Previously, those instructions handle obviously one register per instruction. With this expansion, they can handle 2 registers per instruction. Besides that, there is one interesting feature called the hint bit. You can program the referencing internal state for pop operation rather than unconditional accessing stack memory. That's a really performance optimization, I think. And lastly, the APX feature also introduced additional conditional conversion for those 2 instructions. And those, well, there are other sub-features like a flag deprecation, but you can look at the spec documentation. But overall, the feature that I mentioned is separate from the register extension, but it is expected supported by compiler. Let's look at the compiler status as of now. Looking at those 2 major compilers, both now seem to release to support the APX flag option. Last year, I can see now they are deployed into some distros. GCC also has some follow-up in this year to support the additional features. So looking at their repositories, GCC seems to have a wrap up their support, and LLVM still seems to have some development to fix some bug. But overall, I think it's fair to say both are pretty much ready to support new registers as well as those APXs of features. That's pretty much it for the context here. Let me move on to the potential usage and possible application approach. So considering usage model, I can three possible cases I could think. It could be more than that. I appreciate your suggestion here. First, following the floating point and a vector register model, the application could be pretty much into some libraries. For instance, the crypto library embrace vector register, AVX512 recently. I also posted another example that actually demonstrated a case with Rubololi. That's pretty much the very limited application. The second usage we can think is relaxing the kernel stack usage by scratching those new registers. Compiler can produce some estimated stack users. As mentioned, there are versions that actually support APX flag. So the comparison is possible between with without flag. So the earlier kernel version, I checked that, and then I saw like some percentage, like 3% overall. But I don't think highlight that number that much, except for a couple of points. One, it actually showed compiler produce different images with without this format. Oh, sorry, without this flag. Number two, it actually shows some potential. It actually shows some non-zero value, which means that there is a possibility to save the stack here. But it's static analysis. Static analysis itself is just a reference point. It does not reflect the real usage. We really need the runtime data. But also there is a code dependency on x86 so it's much more than like a 10% changes, but on some other random driver, I say like a 1% very minor change. The last area to think about is quite a generic one. So there's a potential benefit of recompilation, expecting compiler to pick those features, which are essentially a compiler-assisted feature that are applicable by broadly by recompilation. So given those brief usage sketches, let me a little bit delve into the application approaches. I think that there are three aspects here. One is how to transit the state context switching mechanism. And the other two is how and where to apply. So we already have a XSave mechanism to switch user space APX state, which are exposed through, again, XSave non-compacted format. On the other hand, legacy general purpose registers are already switched on our entry and exit point. Taking that mechanism for those new register context is possible, but I think it needs some ABI consideration. I think since XSave ABI was established, I think it needs to preserve established ABI. Another question is currently extending whether to extending the ptrace register structure. That is currently saved for the legacy general purpose register. Surely this entry point to switching is more complicated than XSave. So maybe that's the reason taking XSave mechanism for user space support perhaps makes sense. But given there is a context switch mechanism, I could think and then develop this discussion more towards the application model. Using XSave is relatively simple, but it is a restriction in the application. That approach is aligned with the floating point and a vector register usage in kernel. That is established API, as you know. It first checks whether register set is available, and then it correlates usually by the begin function and close by the end function. During the usage window, the preemption is disabled, right? So the application scope is a bit limited in this sense. On the other hand, entering
Hey, Chang,
point.
I noticed Peter has his hand up. Did you want to? You have a question, Peter?
Go ahead, Peter.
No, we can take that at the end.
Okay, go and keep going, Chang. Thanks.
Okay. So I think that like I was talking about API, and then so the application was limited, but on the other hand, the entry point switching approach allows more freedom, more flexibility to use those resources. There is no API obviously required for currently using legacy general purpose registers. It may apply the broader scope with a recompilation even, but on the flip side, you have to think about how to interact with the old system, right? So recompile the binary will not run smoothly on those systems. So kernel should provide an option to choose one of the two paths, basically, so then eventually increase the image size. So that's a potential side effect. So in summary, there are two kinds of opposite approach I could think of. It is following the former establishment, either floating point or a vector register application, or the other approach is for the general purpose legacy general purpose registers. The former approach is more restrictive in application, but its side effect is somewhat manageable. The recompilation option may bring a APX benefit in the broader scope, if there is, but it's a side effect has to be thought carefully. Previously, I tried to summarize those two on the list when I initiated the discussion, and Peter Z also gave us some interesting insight here. So currently the FPU API requires preemption disabled. The question is, can we relax this preemption requirement? Preemption disable, relax the preemption disable prevention during the uses. I think it's possible, but the question is, the kernel need some space to save kernel IPX states. Then XSave could be an option, but it's a bit wasteful if you are saving the kernel APX state only, because you have to pay tax for the mandatory space that is for the header and the legacy state. So even it's a kind of a 4 times kernel memory consumption to save about the 100 byte. So yeah, that's it. Let me wrap it up. And then one disclaimer I think here is that there's no the data point yet demonstrating its benefit other than documentation. So you might wonder what's the measurable impact for sure. However, I think these are a couple of established approaches are worth referenced, and when it comes to in-kernel usage consideration for today. Maybe another option could be thinkable, but I appreciate your feedback and other suggestion here. Peter? Hey, Peter, I think you can go.
Yeah. So I think personally that if we're doing this, in the kernel, at least on a like recompiled kernel basis, which I think is probably almost certainly going to be the favored option. I think at that point, it absolutely makes no sense to try to go out and put the eGPRs into the process X state area on every context switch. Rather, I think masking that out in the context switch and just exposing it to the signal handler and ptrace in X state format is probably the way to go. It doesn't mean we have to change PT regs, because we already have a concept for a extended PT reg struct, which applies perfectly fine in this case. We would just push it onto the extended stack frame that PT regs is part of, but not the whole thing.
Actually, maybe we could just back
Yeah,
up.
but you still have to save it on context switch.
So maybe we should back up here just a little bit.
Actually, you don't, because we don't save the existing GPRs on context switch because we already have saved them. They're already on the task stack.
Right, but if you do not expand PT racks and save the extra GPRs, then you have to save it with the X state.
Yeah. No, that's not what I meant.
There's only two options. So you can either you expand PT racks, which is kind of stupid because it's ABI and brings a lot of other trouble. So having it, and then the only other option is to do it with the rest of the X state on context switch, and then restore it before going out.
So maybe we can back up and break.
Then you have to do nothing in any code path.
So maybe we should back up and kind of set a little bit of the base here first. I think the first thing here that we kind of went unsaid so far is this is recompilation, right? So the way we've normally done these things in the past, like when a new, like when AVX 512 showed up, is that we use it in very limited places in the kernel, like your kernel FPU begin and end sections that you talked about. But like we use it in crypto code, and we only use it in places where like we had another option to use it, or that we had some other way of doing that operation without that ISA there. And so this is really, really different than that, because this would be like, your pervasive use in the kernel, for example, and like when you switched on entry, that means that like the whole kernel would be compiled using this, and it wouldn't be an option at all. Like it would be a different binary kernel that would only run on AVX systems. So I think that's kind of, I think, question number one for the room here is, Cheng, you went down that rabbit hole, pretty far here, and that's a really good thing to flesh out. But I think the first question is like, is there a place in the world for a kernel that uses a new Intel CPU feature that's compiled that way and only runs on those systems? Or is that just like a non-starter to people? Would anybody actually use it?
And the most
in
important,
a data center, yes.
Yeah, but how do you distribute two different kernels? An old and a new one.
Right, but in a data center environment,
for the distro people.
Yeah, they're here.
They haven't
The,
streamed yet.
the more interesting question is, how much performance gain do you get
Right.
out of a kernel with these extra GPRs enabled? I
Could be
mean,
worth
if
the
it's-
effort.
If it's, I can see that user space might massively benefit by recompiling, but then that doesn't mean the kernel has to actually use them, unless there is really a massive performance gain involved, and that needs to be demonstrated.
But you have the same problem with only user space recompiling, because then you have to deliver 2 different user space.
I mean, that's the people who care about the extra 10% of performance, they recompile their user space.
Yeah, I would say
And
just
if,
let's
if-
focus
if you're
this talk
compiling,
on
if you're recompiling user space, that is actually a much bigger job than recompiling the kernel. We have had situations in the past where people would already distribute multiple kernels, like, for the i386 PAE stuff. But what I want to say is, I also want to comment on your PT regs thing. We already have the stack frame that we already have is actually already larger than PT regs. The ABI part of the stack frame is not just PT regs anymore. So that
I know.
we can push it into the stack frame and without making it part of the user space ABI PT regs, because we can move it into the X state position at that point. So we can do this just fine with without having to deal with the ABI aspect of PT regs.
Yeah, I agree, Peter. But I mean, we only want to saving it on entry, like we do the save the current register state on transition from user to kernel, like we do the current register state, makes only sense if we actually use it actively in the kernel. If you have a full recompiled kernel which makes use of those registers.
Oh, absolutely.
If you
yes,
don't,
no,
and
absolutely.
Just use it for some crypto or whatever interesting place where it makes sense. Then
we'll
then if
for
state
that
is
for
more
that model, it is no different than the FPU state. Yeah, we're in violent agreement here.
okay. I mean, and what we really need to have is numbers. Does it make of a recompiled kernel? Does it make that much of a difference that it's worth to actually have a separate kernel which has these larger register states?
Yeah, I agree with that point.
If you only get 0.5% out of it, forget it.
There's one other concern that I have, which is that the current entry code, it pushes the GPRs and clears most of them. That's a defense in depth measure for a lot of these security issues.
Correct.
So if you don't do that with these, then that's now a great avenue for people to go and get their arbitrary pointers into the GPRs.
No. If the kernel doesn't use them,
if we don't use them, that's not a problem. We don't clear the SSE registers on entry.
We don't clear the FPU state either, because it's not used in the kernel.
But I think, David, you're saying on the presumption that we have a kernel compiled to use these as
yes, then we have to do the same thing what we do with the current register set.
Yep.
I mean, obviously.
There is a slight difference. I mean, it's probably not that big a deal, but the floating point ones cannot be used directly as memory references, whereas these can. So that makes them a little bit more powerful from an attack perspective.
Yeah, but if they are not used in the kernel at all, then
then you just have to find a non-architectural instruction, right? You have to find a sequence of bytes that.
Yeah, I mean, we get there.
Yeah. So the problem you have is with a kernel, a kernel compiled for user space use of it running on capable hardware, because then you can speculatively execute non-architectural X2 instructions and you have lost.
Fred entry point. The Fred entry point is defined as a speculation barrier, so it shouldn't be able to happen.
That means you can't dereference it immediately after hitting the Fred entry point, but it doesn't mean it won't hit 3 functions deep into a syscall handler. The problem is having the registers around.
I mean, if you're not using them anywhere, there are no such instructions.
Transitive execution can pick up instructions that are not architectural.
So this is, I think, a very good topic, but I think we can boil it down to say, if we have support in the hardware and this feature turned on, do we need to clear them on entry or not, even if the kernel isn't using? That's a very interesting question and probably something we need to explore going forward, but I don't think there's a super clear answer to that in the room. So let's table that.
That's something for
it's matter of speculation.
Yeah, so let's table that portion of it. I would like to get back to, like, I mean, the larger question here is, like, is there a place in the world for this APX only kernel? Like, and I think I heard somebody say this, I think I heard Thomas say, hey, the performance gain better be good for this thing. So I think that's part of the roadmap here that Cheng, you have to listen to is, so the other question is, would we ever want upstream support before we had a good idea what the performance was? And I think we've got an answer of no, right? We wouldn't assume that this was going to do good. So, and we would have to have some real performance numbers.
You may want to do so. The thing is, you're not going to get good performance numbers unless there's an easy way of doing it. Okay, maybe it's an RFC series post or something like that. But having one top level kconfig that's, hello, I'm APX. Please compile me with the right flags and does the correct entry and context switching. That needs to be available and work well enough for the hyperscalers, the big data centers, to be able to take it and experiment with it and give you an answer of, yes, does it get better or not? So the work needs to be done, even if it's not going to be taken.
Yeah, but we can do an initial assessment even without reaching out to those people, and only if the initial assessment gives a significant gain, then we can actually think about it. That step to go out to the people to test it.
Totally.
And I was hoping we get a couple of them. Yeah. Does that pique anybody's interest in the room? So the other thing is, if I was hoping people would hear about this and say, hey, like, we might want to go test that in our environment when this hardware shows up. So just a kind of heads up, Cheng, what hardware generation is this showing up in? Do we know, or have we seen?
Yeah, there's a documentation, Nova Lake and the Diamond, both the client and the server. Yep.
Okay. So the next generation stuff, it's not out yet, +1.
There is one extra complexity to building a kernel straight for it. Is the fact that APX isn't actually one thing; it's 2 ABIs. Because there's a magic CPU ID bit that says, oh, actually the NDD and NCI and NF capabilities are not present. The compilers don't currently understand this, and if you ask them for APX, they will generate code that won't work on some vendors' processors. So if you're building a kernel for this, you actually need 2 flavors of the kernel, the blue flavor and the green flavor.
Or we just say, or we just build the kernel for the one that supports both, and we don't boot if it doesn't have both. It's nasty, but I mean, that's the hack to get around it for testing, at least. So, yeah. But good point.
But the thing is, if you're looking for the maximum performance gain, you absolutely do want to be doing the conditional conversion of the if statements, because that's the thing that potentially vastly reduces your basic blocks and your complexity of logic. If you're going to see wins, that's where you're going to see wins in the kernel.
Right.
Well, for testing, it's not really a problem to have, different options for people to test whatever. The bigger, for the bigger issue, it really comes down to, yes, we need the compilers to catch up and make sure that, and so that we have the granularity we need.
I have it on good authority. It's being worked on, but it's still slow progress going.
And have any other vendors said anything about their support for this? I don't think anybody has. So darn.
One VP from AMD has said something generic on LinkedIn.
Like they don't hate it.
That they're aligned with the direction of the industry, or words to that effect.
Yay. Okay, that's all we can ask for. So we can pause there. We got a couple minutes left, but see if there's any other questions in the room before the coffee break.
Sounds good.
Okay, thank you very much for the feedback. I think the next step is
Yeah, thanks,
clear.
Jake.
Goodbye.
Thank you.
Thanks. Okay, and I think we're up against a coffee break until noon. See everybody back at noon.
I did actually have one question, but it's mostly to Peter, if he's still around. Is there any opportunity of using push2 and pop2 in code that otherwise is not using the rest of APX? Because the one thing that doesn't depend on that is the hint bits for the memory reduction. My question is it possible to use the hint bits on the regular 16 GPRs without the rest of APX turned on? Because that in itself might be worth looking at.
Jet lag's not bad here. I don't know. Unlike Europe, it isn't.
I have to admit I am not entirely sure if you have to enable the eGPRs for that or not. You definitely, there's obviously no requirement that you use the eGPRs when you do them. I just don't know what the control bits do. I will look it up.
I have to admit I'm staring at the spec right now and I can't figure out if it's yes, no, or maybe.
So Andrew, your question is like that the hint bit is applicable for legacy GPL as well. Is that your question?
Well, so the hint bits are both are in the push2 and pop2 instructions, but also in the original single pop. So obviously you can't use the push2 and pop2 when you've got the rest of it turned off, because it'll take a UD because it's Rex2 encoded. But for the ones that aren't Rex2 encoded, will the hint bit still work for improved performance and reduced memory or not?
I will look into that for you.
Because the thing is that is in principle a compiler transform work on older hardware, I believe, which might mean it was safe to turn on generally. And if it does get you 2% or whatever from reduced stack accesses, that still might be a worthwhile thing to do in isolation and separate to the rest of the APX enablement.
One interesting thing that kind of comes to up in that one actually never mind. But yeah, I'll find out for you.
Thank you.
Initially using the and then somehow switch it.
Oh wait. Okay,
Thank you.
together from two things, right? There's the kernel people that that eventually gets. Then there's the memory that we save it to, which is a memory export, easier, but it really is. We can extend that back to the country, but then we reconcile that. Yeah, but we can technically end it. But then there's the question that we and reconciling the speaking regs thing, which is like this record versus that's and then reconciling that with excellent. How old? So fine.
Well, now you have to differentiate between one and the other. Oh, you're going to
Yeah. So imagine that we have whole users. It doesn't. It's saving it for the user. It's saving it for itself. You just have a loop. A little bit forward. Another way to see it is that we could and people show up. And it will have to be yeah, you basically like
I said I'm.
you're still.
I said the same thing.
Yeah. The next slide. Let me show you, right? This is, yeah, this is actually not a key, but not more. Yeah, this is actually DPK and it has like a CSS writing system. And I was no, like 3D models. Yeah. One day I want to really invest in like really thank you. There's a thing called like QML based framework for writing like frauds and stuff. Okay. And I really want to make it so. That's what I was like really nice pieces for really nice, you know. Yeah. So for yeah. This is stuff. On that live actually. Yeah. I don't know if you had the full context, but basically. Oh yeah, we talked about it before. Yeah, so we basically learning to live action. Yeah. Yeah, I haven't actually looked at how much it is for yeah, I think thinking about it is something that you can say. All that. Just right there, package that when we use the that would like to say that one is then in one place on the other one not sure. Yeah, that's what I think. I mean, you're interested, like some things are things. Just that we found so that we have a way to go out. Yeah, no, it's something like I think even we can maybe figure out something to package in my pack. I think one of the things is to have the person who really have that. I almost wonder if we just have like a similar branching model, or maybe we can use the live branches except say, okay, build modules, and then you just build your very similar to because yeah, it's just you know, there's like this whole model of model, cumulative model that kind of top of that. And that's just always sometimes this is okay because I'm going forward and going backward. I don't run the removal callback unless I'm completely removing and I think in this case, all that infrastructure is now getting in the way. Actually, we don't want to use any of that. Anything. Like, I don't even think we use the model. What you're going to do is kind of interface and modules can be say ASI. Okay. Yeah, you could, yeah. So you could even arrange like the ASI at this point. Explicitly replace one, saying that you can't really apply multiple ASI. Yeah, there's lots of little relationships. This live path or this package brings other package. Places it or divides it, which is like basically that's how live path is. Every live path replaces and divides. Yeah. Eventually, but I think the general solution is the target.
Actually, the other thing is, as long as we can get something in terms of the work around one way or another.
Yeah.
Before, they might,
Yeah. So I imagine there's this state thing. I don't know if there's a way that we can interact with it. What? Dropped in a little query like state. And then you can drop in a hook in the actual code of the kernel, and it would say, oh, if this is an inside line, make sure to put clear swap if this is there for your backing power.
the other thing we could also do is that you have this, you said,
Oh, yeah, you can totally go forward.
yeah, only thing matters is that make sure you
Yeah.
and that's always the because it's always but that's what you do.
Yeah, it's just that weird that rollback from one live patch to the last live patch because the previous live patch doesn't know that the next live patch. Oh, I need to bring it up.
The thing is, like they were saying, was about in the previous set, I think that people everyone needs this. Almost certainly, the communication is very big. But I think you already have a, we're talking about like, the people are like frantically desperate to be able to live back. Which I think is the thing. What actually said? The code that we run in foundations in universities. Oh, they don't do. No, they just want to be able to add on. The new mitigation requires, I guess the thing would actually happen. Oh, we need to try this like, it's all up, we don't have enough for it, so we do this. Dances with dance that had to go on the second half of the crash line. It's actually, it should be easy, but
Yeah, Google's packaging system just really put up first.
Oh, okay. Like our system, Ah, and literally. Oh, this is more. Okay, they're really easy. They also. They can be. They are. Very creative. That's kind of the. But the thing is, if you want to go, you don't want to go really. Yeah, and then it does all the stuff you just started. And then, you know, that. And anything for. It's very hard to guess whether that like group or what. Yeah, I don't think because all three of them. Yeah, yeah. So it is. For the group. 256 times. I always question that one.
1, 2, hello. Okay. All right. I'm still here. I'm still trying to get ISI in. I think this is the third LPC presentation. It's my second LPC presentation, my fourth Linux conference presentation. So maybe we're getting there. We'll see. This is going to be a little bit more of a status update than I've hoped. So on the schedule, it says ASI is ready as the title, which is true in the sense that I think I'm claiming that we're now in a state of, I think we've proven together that the idea works. I think we're over the point of median uncertainty about whether this is something that makes sense to put in the kernel. It's just a case of getting it in now, I think. Maybe it's a big claim. It's not ready in the sense that the code, I expected to be able to point at a branch with here's everything as I think it should end up in the kernel. And I'm actually not there yet. Coding takes more time than you think always. So yeah, I'm not really going to reintroduce ASI. So if you are new to this concept, I think we don't really have time. It normally takes me about 15 minutes to explain what this thing is. If you don't know what it is, the basic idea is to try to run the kernel without user data mapped, without re-architecting the whole kernel. So we have 2 address spaces. One has everything in it that today's kernel address space has. One doesn't have user data. If you touch the user data, we take a page fault, transition, do some flushes. That means that we don't have to random parts of the kernel don't have to be aware of these 2 address spaces. It's more or less completely transparent. But if you didn't understand that, go to this fancy new website, linuxasi.dev. I did some web design. It's beautiful. It's not super up to date, so also email me if there's things that aren't clear, and I should try and keep it up to date. And there's the best resources are links at the bottom to previous talks I've done where I've actually tried to explain it properly. Oh, it's working. Okay, so yeah, I also want to do a bit of motivation, keep people excited about this wonderful thing. Something that occasionally comes up is people are like, oh, you're still working on CPU mitigations. You mean like Spectre? That's 10 years ago, man. Haven't the CPU people fixed it yet? They have not. And what I'm going to argue here is that they're not going to. So if we look at these things in a very, very abstract sense, there's kind of 2 sides of it on the whole. One side tends to be that the attacks involve controlling the branch predictor, the attacker controlling the branch predictor when the victim executes. And then the other side is that the victim leaves behind something in a side channel, the attacker steals it. It's kind of more complicated than this, but in a very abstract way, this kind of makes sense. So that one direction, the CPU people are doing good work, I would say. There's a bunch of partitioning things going on in the branch predictor that in practice on new CPUs is starting to make it pretty hard to do this. But in principle, you can't actually solve that. You can't actually have a secure branch predictor. You're always going to have mispredictions. Otherwise, it's not a branch predictor. It's just a CPU. And there are always going to be insecure predictions, right? That's always going to happen. And then the other side is side channels. I don't see any progress on that. I don't imagine anywhere you could not have side channels.
Yeah, and I'll also say there are 2 sides to this. The CPUs are getting better, but there are pieces of mitigations that we missed, like the VMscape stuff recently. The CPU guys on that one said hey, we told you this could happen, and us on the software side were like, yeah, we think it's pretty unlikely, and then somebody puts together an exploit that shows that it was more likely than we thought. So yeah, I'm just giving you more motivation than just the CPU stink.
Yeah, I'll come back to VMscape actually. So yeah, the point is, I think now as systems software people, we just need to see CPU security as a part of our job. It's about software architecture now, and it's going to be that way forever, I think. Even if they were to make us perfect CPU, we've probably still going to be running Skylake for a long time yet. So it's a good CPU. We love Skylake. The other thing people are saying is, can't you just unmap the KVM guest memory, which Nikita Husser is doing? And yeah, you can. It's great. Kind of. So if you can really get all of your secrets on your host into this memory that's protected by this mechanism, and you can run your stack on a platform that has this mechanism, then honestly, I think it's the way to go. I think for cloud providers, this is maybe not exactly the guest MFD thing, but something of this nature is the end game. But we're not that close to that. And also, don't tell my employer this, but I don't dream about cloud providers every night. I'm more of a Linux guy, and I hope some of you guys are too. So yeah, I want to solve this problem for everyone, not just for Google and Amazon. As much as I love Google and Amazon. Yeah, so hopefully I've convinced you that we still need ASI. Bit more excitement generation. I'm going to brag about how clever I am because I mitigated VMscape before I knew about VMscape. And it's what Dave was just talking about. And I'll take this as an advantage to show you how ASI thinks the world, the problem space. We think about the world in terms of domains. Some domains trust other domains. So KVM guests trust the VMM process. You can see my pointer, right, by the way? Just about. Everybody has to trust the kernel, otherwise they better not be running on this machine. VMM processes and other processes are mutually distrusting. I guess you'd hope that you can start to create more trust boundaries. Like ideally, I think Google would love to be able to say the VMM trust the guest. I don't know if we're there yet, but yeah. So this is kind of obvious, right? This is just like, I'm probably not blowing anyone's mind with this way of thinking about things. But the thing that ASI lets you do is have this like obvious model, which I will in a moment argue makes VMscape very obvious. If you think about things this way, VMscape isn't a surprise. It's like, yeah, of course you can do that. But we kind of had this motivated reasoning where like designing our system according to this simple model is just really expensive without ASI, because without ASI, you're transitioning between these domains all the time. And if you're doing expensive things on those transitions, you're trashing performance. With ASI, I just use this abstract term of a domain. And so you might think that this box represents the VMM process, but it doesn't. You can enter the kernel within this box. That's what ASI does. I don't know. I'm getting some blank stares actually. Does that make sense when I say that? Okay, I'm seeing some nods. Let's see. Anyway, let's just walk through how ASI mitigated VMscape. So, and this is kind of illustrative about some of the implementation work. So let's say you're in your QEMU or whatever it is, then you get an ASI exit. So note that this transition doesn't represent a syscall. It represents a syscall, for example, and then the kernel touched some user data. We took a page fault. This transition is called an ASI exit. So what do we have to do when we do this domain transition? So we're going into the kernel. The kernel is afraid of having its branch predictor controlled by user space because it doesn't trust user space. So we have to trash the branch predictor. The user space is also leaving behind secrets in the side channels, so the kernel can steal them. Obviously, who cares about that? The kernel can do whatever it wants. We trust the kernel. So the conclusion overall is we need to flush the branch predictor on this transition. Let's say then we go back to the user space, and basically it's the opposite story. We don't care about the kernel controlling the branch predictor. We do care about the kernel leaving behind secrets in the side channels, so we flush like load store buffers, whatever it might be on that CPU. Then we context switch to another process. Just to avoid any conclusion for people who might be reading the code, this transition isn't actually possible in the code that you probably have seen. Just as a simplifying factor for the implementation, you actually always ASI exit first and then ASI enter. But that's just a simplification for the initial implementation. So let's forget about that. So yeah, if you're switching between processes, they are mutually distrusting. We have to flush the branch predictor and the side channels. Let's say we go back again, just keep the story consistent, and then we do a VM enter. So the VMM doesn't trust the KVM guest unless you've got a really nice stack. So we need to flush the side channels. Let's go the other way. We don't want the KVM guest to be able to control the branch predictor of the VMM. So we flush the branch predictor. Oops, oh, we just mitigated the VMscape, right? So this is what I'm trying to say is that like, now we get to think in this very principled way. VMscape was obvious. I mitigated it before I found out about it. The code that you'll see in the RFC mitigates VMscape. And yeah, so ASI is like, lets you get ahead of attacks. So yeah. Pause for applause. So yeah, this is just what I just said. Okay, so that's kind of in terms of like me talking and showing off. I'm done, and now I want to talk about where we're at. So yeah, I think I've solved all of the big abstract scary problems about whether ASI is viable now. And now the big problem is how to get the code in. if we go from like Linus's master today to an ASI that you can kind of run, I actually don't really know, but it's something like 100 patches. Nobody wants to review that. Yeah. So well, I did the next best thing, which is I just like lopped off the first chunk and was like, here you go, guys. So it was 21 patches, which was like the stuff to set up the direct map. And Dave was like, no, you can't just chop your patch set in half and post some of it. We need to merge code that does something. So that's what I'm trying to figure out right now. So I'll talk about the ideas I have, and please raise hands if you have ideas. So I described this model where we have this kind of domain model. And I mentioned that when we're transitioning, I mentioned that like inside this red box, for example, there are kernel entries and exits. So there's actually invisible state going on here. And there's some code to manage that state. And that code isn't entirely specific to ASI. So one thing we could do is try and get that code in, because there are already some stateful mitigations in the kernel. So I think, well, VMscape is the obvious one. But then there's also some Spectre v2. I think it's something like if you've, on a context switch, IBPB, but only if we went into user space since the last time or something. And there's another thing that's like, I think it's, I wrote L1TF there, I think I might be wrong, but it's something to do with like flush L1D if we've been to user space since the guest or something like that.
Yeah, just by stateful, you mean like for VMscape, for example, we worry about running user space after we've run a guest.
Yeah.
But the transition out to user space, we don't want that to be too expensive. So we only do that when we're going out to user space if we've run a guest.
Exactly.
That's why it's stateful.
Yeah, which is kind of fundamentally the point of ASI as well, right? It's just, and it just introduces new state transitions that let us dodge it more often. So I coded this up, and it just like, I looked at the patch set and I was like, doesn't do anything. It doesn't clean anything up. It's like introducing abstractions and churning everything around, and I don't know, I don't really like it. So yeah, I'd hoped that I would find a way to dodge more flushes, but without ASI, I couldn't. There might be some like really rare corner cases where like if you have a certain set of mitigations enabled and you like exit a VM and then context switch before you go to user space, and but these things just, I find it very hard to believe I'd be able to find a workload where I could measure the performance benefit of that. Oh, hello. I can't read that. Can anybody?
Whoever was raising their hand, go ahead and ask your question.
So my question on this is how this compared with LAS.
Is that the I don't think I'm familiar with that. Could you?
LAS
Go ahead,
is
Peter.
linear address space. LAS is linear address space separation. It's the shortcut that basically encodes user space in low addresses, kernel in high addresses, and it will terminate page walks before hitting the page walkers. My opinion here is that LAS and ASI are not solving the same problems. You ideally want both, but they are not. They're not solving the same problems.
Yeah, I think there may be some confusion about what it does, because you said it unmaps user space, and I think when people hear that, they might think oh, well, you said it unmaps user memory.
Yeah,
and that's different from unmapping the user portion of the address space. So what you're mostly talking about is when you have user data mapped into the kernel direct map. This ensures that you can't normally reach user data mapped into the kernel mapping. We're not talking at all here about the user space portion of the address space.
Yeah.
User space uses that.
Yeah, we're talking about I shouldn't say user memory. I should say user data. It's a question of the data in the memory. It's not a question of addresses at all.
That makes sense.
Okay. So is that answered, or should we carry on that topic? Okay, I'll move on.
Go ahead. No, that answers my question.
Okay, cool, great. Yeah, so the next area where it seems like worth exploring to try and find a smaller patch set is the refactoring of the page table code. So I think in terms of like page table libraries, what do we have? We have vmalloc, We have the init64.c, which like sets up the direct map, does memory hop plug. We have setmemory.c. We have the MMU gather code. We have another one I can't think of.
KBTI code.
Right. Yeah. LDT code. So yeah, and the patch set, this like 100 patch set touches the init64, touches set memory. That might be it actually, but maybe refactoring those might be a way forward.
So, and I think you're talking about like you have a larger problem here than KBTI, for example, because and your basic problem here is that you all of a sudden have two sets of page tables.
Yeah.
Because you have your protected set and your unprotected set, and you page fault the switch between them. But all of a sudden we have, when you make a change to the page tables, you got to figure out, if and which of that two sets that you make the change to. KBTI does this, but it does it in a pretty hackish way underneath existing APIs. And I think you need to do it in a more generic way than it does, because I think it only has to mirror PGD changes or something. So it was pretty surgical in where it touched, and this doesn't have that luxury. So yeah.
As well as having two page tables, there are also times when you want to say, map this, and you better not allocate anything because I'm in the allocator, or you can't sleep. But you shouldn't have to. So like I come into situations where I'm like, oh, I'm calling this function which might allocate. I know it won't allocate because I'm very clever, but actually it could. And if I would like the consequences if I'm wrong about that to be predictable. Yeah.
So we do have a lot of code doing user space page tables, and the kernel space page tables are pretty hacksy all around the place. So if we would be able to merge it in a way that might give like managing multiple page tables out of the box in a sense.
Yeah. So yeah, I don't know how hard to try at this, right? I don't know how.
I think it is, yeah, but
one thing I'm doing in the patch that I'm preparing right now is just taking out the vmalloc.c has some, I think the simplest page table library. And so I'm moving that into a header and reusing it for a small subset of this. That might be a starting point to go from there. And that's Arch generic, of course. I didn't mention that actually, but like, so which ones did I mention? I think actually vmalloc.c is the only, and the MMU gather, the user space one. Those are the two generic page table libraries. But the x86 ones don't look that different, right? Yeah, and then it's like the memory hot plug or boot setup. The code, so I think it's like making assumptions about how we've architected x86, but it's not making assumptions about the x86 architecture.
To start with, set memory always takes the PGD log for anything.
Yeah, that's what I mean, right? So that's not an x86 thing. That's a
no, it's x86 thing. But
it's x86. It's an Arch x86 kernel tree thing, but it's not an x86 CPU thing, right? So
that's how set memory is implemented.
Exactly. Yeah.
It doesn't have to do it, but I think it's historical.
Yeah. So I think I probably just have to try things and get a lot of feedback and see what people think about that. But yeah, I don't know. But before I move on, I'll see.
I mean, the idea of having a more thorough, well thought out page table library is a good one. I mean, yeah, everything that we do is ad hoc. It's crazy. It'd be nice to have more structure there for somebody to actually look at it and take a more holistic view. And I think one thing you were dancing around is there is a lot of x86 code that is just dealing with page tables. And there isn't anything really x86 specific about it. You could have taken that code and just lifted it over and compiled it on PowerPC and it would probably run. But yeah, like the concepts are not specific to x86. And we have the benefit on other architectures of everybody using the style page tables. So yeah, I think I would love for some people to look at that a little bit and see if there's some libraries that we can abstract out. There's certainly some low-hanging fruit there.
Yeah, I mean, I just want to say you'll get a lot of support from the MM folks if you're looking up the APIs and reduce the look, we've got 5 functions that are essentially identical to each other, just with the names of the variables changed. Yeah, I don't love that either, but Linus does. Linus thinks it's great.
So
This is the thing. I'm a little bit timid, right? Because I think, the people who wrote this code were quite clever, and I'm a little bit. I get a lot of chest and fence feelings, right? Where I'm like, okay, they look similar. Maybe I could merge them, but maybe I need to be bolder about just trying it and seeing what people think.
I do not think people were being that clever when they wrote the code, to be honest. I mean, it usually is the shortest amount of time it took to hack the thing together. And it is a lot easier when you're writing page table code to only think about your architecture and do it in code that you control.
Mm-hmm.
And it wasn't necessarily the best place to put it. It was the easiest place when you're writing the patches. So I don't think it was really designed.
How dare you speak that way about Linus's master's thesis?
Okay, so that sounds overall like it's. Oh.
So the one comment I do have on the one is that yes, on surface these page table formats look very similar, right? But there are a lot of nitty-gritty details in where they deep down, like especially if you look at I don't know, like granule sizes on ARM or on like I don't know, different terminations of sometimes even different feature bits on the different levels you may have, right? I don't know if making something that is more generic than at least the architecture you're sitting on is going to be substantially more readable and maintainable. Like you can probably abstract it, but I think then looping yourself through these abstractions while you're trying to debug something is going to be helpful.
But we do have that for the user space page table already. Like generic MM manages user space page tables in an architecture independent way with some hooks here and there, but
I think there's two levels here, and there's definitely bits that can be shared. Architectures, the kernel page tables. There are things that are quite different. Like for example, on x86 and several other architectures, you have per process page tables because you have like one base page table. ARM64 has separate page tables for user space and kernel. And that means that the management of that looks very different at that level. So there are going to be bits that you can't pull out, but there are absolutely bits that you can share.
Yeah, things like our PGD propagation. Like when we make an entry in one PGD, we got to take it to everybody else. And you guys don't because you don't have it shared in the beginning. You don't have a separate one per process to begin with. So you don't have the propagation.
I'm just curious, like we keep talking a lot about page tables, like how many patches of your patch set is that? Actually, like that point. No, no. What I'm trying to get is like, for example, the last point. I think I suggested something like that. Would it actually like make it more feasible to get something merged than just like shuffling code around?
Yeah, well, this is what I'm going to come on to in a minute, which is.
I mean, talk about page table generation is great. We have it at every LSFMM, and not that much happens.
Yeah.
So,
yeah. So well, maybe that's a chance to move on to the next one, which is. Oh, yeah.
Let me just ask one other question around in the area. What if it wasn't Arch x86 code that was doing this? Like, how much of this could be done in generic code? And we have a little bit of backing for x86 there, but like, could it be done in generic code mostly?
You mean ASI?
Yeah,
I think so. Yeah. So actually, the last thing I posted is doing exactly that. So yeah, some of that change was about refactoring set memory.c, and so I guess that's architecture specific. The implementation of it is, but that only thing about that's architecture specific is the page table management itself, right? The API is generic. Yeah.
Well,
to answer your question,
also what do you need to do to flush the branch predictor and the side channels? That's also architecture specific, but has a generic hook and a position.
Yeah, that's actually CPU specific, right? But that's really easy because they're all. That's like there's two pieces of straight line code that have to differ per CPU basically, and that's fine. It's CPU, it's model specific.
I know, but like the way you would handle this on ARM is very different from the way you would handle this on x86, which has instructions. On ARM, it's just, I don't know whether this model actually like translates to ARM that well, the ASI exit and enter, right? Like
think the only way it could be fundamentally different, and I'm not well prepared to answer this question, but I think it would be if the mitigations in ARM, instead of being like instantaneous transition or flushes, are like mode changes. But actually, ASI is mode changey in its own way, right? So that works fine. I think it's actually probably generic enough. A big claim to make without evidence, but
they tend to be implemented more in firmware, these sort of flushes, right? Like if than like an IBPB like instruction that.
Yeah, but then if it's in firmware, it's either a global setting that you set once, it's an instantaneous flush action that you do on a transition, or it's a mode that you switch between. And like, well, the first one you can't do for ASI, the second two work fine. So I don't know. I'm looking at Mark here in case.
I think the management of predictor structures and all that sort of thing is entirely orthogonal to the management of the address space. I think it's one thing to separate the two entirely. Yes, you happen to have hooks that might be in common places, but they're entirely separate concerns. Yes, on x86 it might be model specific, ARM it might be model specific. The things that we're going to do are quite different because the model that ARM went for is explicit context tagging, and so the places in which you have to change that and the places in which you have to explicit invalidate are quite different from x86 and other architectures. So this is a combination of architecture specific, model specific, whatever. But that invalidation or management of those context structures is a separate concern from the address space management. I don't want us to conflate those two.
Sorry if I missed this in the context or in the talk, but does ASI permit like a hybrid model where some tasks opt into being isolated or other tasks may be completely unisolated?
Yeah. The code I post initially won't do that, but there's no challenge to doing that.
Okay, so I'll explain why I think that might be relevant. One thing that keeps getting questions about is device or data independent timing. So so basically CPUs have two modes now where in some cases they can go faster, but they might reveal, don't want them to reveal. And I could imagine tying the two together where you're only permitted to turn that off and have data-dependent timing when you opt into the address space isolation.
Yeah, that should work fine. Yeah. I think we talked about that with some Intel people at some point. Like we should be able to go into slow mode and that's exactly what I mean about how instead of being an instantaneous flush moment, it's a mode transition. It's compatible. It should work fine.
Right. Okay.
Okay, so I'll change topics now just to talk about the last point here, which is, so there's a lot of these, the first thing I talked about kind of, I don't think it really works. Second one is like big ambiguous space, which warrants exploration, but I don't see an immediate step forward there. But the last one, luckily, thanks to David, is the helping out the guess MFD thing. Their problem is that at the moment they want to be able to, well, the problem is they don't have a really efficient way to flush the TLB as they unmap this stuff. I have spent a long time thinking about how to unmap stuff without trashing your TLB state performance. So what I've got is I've got a page allocator feature to handle it for you. So memory is protected or not by ASI and is grouped by page block under that property. And there's a GFP flag to give you pages that are or aren't protected by ASI. So David pointed out that I can just flip the thing that provides to, instead of being whether it's protected by ASI, it's whether it's mapped at all. So I won't go too much into it because it's not really an x86 topic, but I've got a patch set that I'm working on right now, which I thought I would have been able to post by now, but it's not done, which generalizes migrate types into this thing called free types, which are just like migrate types with flags. And you can request memory that's unmapped. One of the challenges that I faced, which I didn't realize until embarrassingly late in the process, was then, was that if you don't have it mapped, then the page allocator is going to crash when you pass GFP 0. So I didn't end-to-end test it until I'd already got everything working, and then obviously it crashed. But I already have a solution for that, which I guess will have to squash into the same patch set, which I won't go too much into it because it's not really x86, but it's called the MER map, which is a new piece of terminology which I'm introducing. It was called the EF map, F map. Nobody knew how to say this name, and when you say it, it sounds like you're saying F, letter F map. So I've gone to the next letter in the next syllable in the word ephemeral, and so it's called the MER map. Introducing the MER map, which it basically gives you a way to say, oh, I want to unmap this memory. Oh, but actually I want to touch it. And do that safely and efficiently. So it gives you a mapping that's local to your CPU logically, as in it's a bug to access another CPU's memory region, but it's not. It's actually mapped there. It's physically MM local, so other processes can't leak it through CPU attacks. So it's basically a lot like KMap local page. Here are the differences. So when you use it, you disable migration for the duration of the allocation. Because it's logically CPU local, you don't have to do a TLB shoot down when you unmap. You only have to do a local TLB flush.
Yeah, so on ARM64, the architecture is pretty unforgiving if you don't do TLB invalidation. And I do tend to think personally that this becomes kind of security theater if we're not doing the the invalidation on ARM64. I know others don't agree with me on that, but can we at least have an architecture I can say we always want the invalidation?
I don't think this is, so I'm not
usually uncomfortable with this.
There's no security compromise here because the mapping is MM local.
It's in a page table that's installed on other CPUs?
No.
No, it's
in the same process, yes. But you can only leak it from the same process, which you can read it from anywhere. Anyway, so there's no security boundary violated by skipping the slush.
I'm not convinced at all, but okay.
So you can. Yeah, it's not mapped into any other process. So there would be an exception if you have some internal boundary within your process, but if you don't,
it's more that if you unmap something and you haven't invalidated the TLB, some other part of the kernel is gonna, if it sees an invalid entry, it's gonna assume that it's not reachable, right? And it's hard for me to reason about what states you can get into. You know, when you've got, I don't know, vCPUs migrating around and you've got all sorts of other things happening. You don't know how you got to the position that you're in, and you don't know whether the invalidation was done or not previously.
But it's a bug. It's a bug to access that region in software anyway.
So I was talking with him about this earlier in the conference, and I was not and am not fully convinced it will work, but he has some pretty good explanations for it. So this is a good move the topic to the bar tonight. And
we go into
it through it, I think.
Yeah.
But, yeah, I mean, in the end, you could just do the invalidation up front, right?
Yeah, but it would perform badly. Actually, no. There might also be cases
you can functionally give him what he wants.
Maybe.
Easily.
Yeah.
Give me, Brendan, if you can give me numbers that show it does actually perform badly on an ARM64 machine, happy to have that. But let's not start from the position that it's slow on some x86 box, so therefore it's going to be slow on ARM64, because I'm very nervous about this.
Because also you're saying you guys have the microcode TLB flushing stuff, right? The broadcasting.
Yeah. We have hardware broadcast. It's not a panacea, right? It has lots of other problems, but it's not the same beast. So I don't think performance on one necessarily translates and vice versa.
But let's have an argument later, and we can try and figure out if you can find an example where there's actually a bug here. Even if the TLB is maximally, I'm assuming the TLB is maximally hostile to this. I think I'm assuming that.
But as we're talking about this, how bad is it if you don't have your MER map?
Well, the way I've done it. Actually, I guess the thing I'm comparing it to is where missing the MER map means an ASI exit. I've actually never tried it with missing the MER map meaning a TLB shoot down. And maybe an ASI exit is more expensive than a TLB shoot down, now I think about it. So
I'm just worried that we're introducing more infrastructure and more piles in the patch. I mean, if it's performance, that's important eventually, but that is one of the things we can give up on initially. It can be slow to start.
So the thing I'm using it for initially is looping through every page in the page allocation. So now you're doing a TLB shoot down per page in your order 8 allocation. That's not good. But
I'm just saying, I think like of all the things, like of all the engineering compromises that we have in these solutions, like I think we can give up on performance.
yeah, that's fair. Yeah, that's true. Yeah.
So if it's a pure performance feature, that may be one, like it has to be functional, but it doesn't have to be fast.
Yeah. The other thing that is probably x86 specific is that you can't do a TLB shoot down with IRQs off, which might be a functional issue, but we might not have that problem. I'm not sure. I can't remember.
And also want to talk about shortcuts. We have hardware, TLB flushing now too.
Yes.
So there are shortcuts. And if we said, hey, you can only do this on that hardware to start, that is also another place to make the patch set smaller.
Yeah. But if it's forgetting about ASI, this is only useful to the guess MMFD use case if it's fast, because they already have a slow version. So if it was going to unblock guess MMFD, it does actually have to be fast. So yeah, I think this is something to look at the code for as well. Yeah. In the end,
for the guest MMFD use call, I think the MER is only used for the right part, right?
And zeroing.
And zero. Okay. Yeah.
Which unfortunately we can't skip zeroing. It does. Yeah. It is nice for security for 0 pages.
Let's start with 0 then.
Yeah. Yeah. So that's I don't know if you've already read it, but it, as compared to KMap local page, it's local to the MM physically. It lets you map not arbitrary, but not just single pages, and that means that it's mostly allowed to fail. So KMap local page, I don't really understand why, but we act like it never fails. So I'm not sure why that is, but I'm sure there's a good reason. This thing you have to act like it fails sometimes, except that I'm going to make it that if you are IRQs off and you're mapping a single page, that always succeeds, which is a kind of ugly API, but I think makes it really handy. Then you can use it for page zeroing and stuff without having to worry about because you can't fail page zeroing. Or you could, but you have to reallocate. You'd have to restructure the page allocator in annoying ways. So probably what it would look like is, I'll try and MER map the whole thing I'm allocating to zero it all at once, and then if that doesn't work, I'll do each page individually or something like that.
Are you saying KMap can fail and sometimes we ignore it?
Well, no, I don't think it can, but I don't understand how it can't, because you have preemption on when you use it, right?
I just remember that some implementations, they keep like an array of pages you could map, and if you're out of memory there, then you have a problem. But if you just know that like you only map a single page, then I think
we have a stack of them. You're just not allowed to nest more than 16 deep. So in practice, it just never fails.
But that stack is per process, right?
Yes.
So if you have like 16 tasks.
No. It's not per. It's per thread.
Okay.
So,
that's the
yeah.
answer.
So
Okay.
Yeah.
Okay. So you actually have to literally nest them in your code. Yeah, I see. Yeah.
It's kind of like the kernel stack. It's like, 16K is perfect and we never overflow it, right?
Yeah. Yeah, but whereas this thing, because it won't be single pages, I don't think we can make it big enough that it just never fails. I think it has to fail sometimes, but that should be okay. And I think it will basically be like an allocator that's a ring buffer. I haven't actually coded that up yet at the moment. It's just a dumb Boolean allocator. Yeah. So like I said, sorry for talking stuff in the x86 America conference, but that's that. How long? Are we out of time now? 10 minutes. Okay, so then I'll go through the last thing, which is what I'm thinking right now in terms of the patches. I think the first patch series I'm going to post, I hope to already post by now, would be this MER map thing, and then solving the guess MMFD problem, which is quite a big chunk. The next, unless I can find a way to refactor the page table manipulation, the next series is going to be pretty big, I think. But I think we can get to like ASI that does something in 40 patches. Dave's giving me I guess face. Yeah, I don't know. So I guess I'm just setting expectations here. I think there's going to be a really big annoying patch set at some point. Yeah, but I hope you guys rather I post a big annoying patch set than artificially squash patches commits together.
Yeah, and I mean, like, we don't like big patch sets, but in the end, if we've exhausted all the other options,
right,
and you are plotting towards this a long time and trying all these other things, and you've been ruling out any other ways of doing it. So we may just run out of ways to say no at some point.
Okay. And I mean, like, if I remember correctly, a certain commit about removing bcachefs was certainly quite bigly recent.
Have you run any performance measurements with ASI and with the mitigations that actually ASI takes care of disabled?
Yeah, not with the recent code actually, but yeah, back in like last time I did this, I had some pretty nice performance numbers. I'm realizing that I've always made this a bit harder for myself than I have to, because I've been always being like, look, ASI is only 1% slower than mitigations off. Whereas I should be saying like, look, ASI is 50, 60% faster than whatever else you get on Skylake. Like, again, I could do it. I could say whenever we measure the like full version of ASI against, well, like whatever it is that Google does, which I won't go into, we trend to be like, less than 1% of whatever it is you're measuring as the cost of ASI. But I could say like, let's measure it against the upstream default. And then like David said, you're looking at 20, 30% wins probably. Or I could even measure it against the thing that you would do if you're serious about security, which is on Skylake or on Roam, which is switching ASMT off. So if you're really serious about that, you've got ASMT off right now. You've got SMT off and ASI with this stunning thing, which I haven't talked about, but a later version of ASI will let you switch it back on. So now it's huge in terms of the performance wins. And I don't think I've been trumpeting that very much, because I've kind of, maybe I should be more braggy about that.
Yeah.
And the CPU architects can talk more about this than I can, but I think the trajectory we wanted initially was, hey, we've got these slow mitigations, and as new CPUs come out, they're going to make things go faster. Like, think of the meltdown mitigation hardware, right? Like, things as we went forward in time, the CPUs got better and the mitigations went away or got cheaper. And I'm not sure that's still happening with some of these things. Like, I think like SSBD might be getting more expensive over time rather than less.
Mm-hmm.
So you may actually get better with newer CPUs in some cases. So like it actually works in your favor. Maybe. Good question to ask the folks that know more. Not me.
Sorry, yeah. So bigger microarchitecture buffers. Hello. Yeah. So bigger buffers take longer to clear. That's right.
Yeah, I think you're saying newer CPUs, like, we don't ever make the caches and everything smaller. We only make them bigger. And so our things that are clearing those ever increasing buffers are getting ever more expensive.
Okay. I mean, so this is all I have in terms of, I have this timeline slide, which is actually, I think I'm just going to skip it. It's nonsense. So yeah, I'm kind of done in terms of slides. I think hopefully people are seeing that maybe there's a light at the end of the tunnel. So yeah, the next step for me is to try and make AWS the best cloud in the world. Like I said, it's my true passion in life. And yeah, I think probably the most important next step actually is to argue with Will about the MERMAP, because there's a good chance he's... Yeah, well, I agreed with you at first, but then I remembered that we need to make Nikita's code fast, because that's the whole point of the code that I'm proposing right now. So
I don't know that it's slow. Show me.
Yeah, true. Yeah, okay. I should at least measure it first. Yeah, that's a good point. But I think it will be. I think it will be very, 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 very slow. But yeah, I should prove it.
And I think we said this in email, but I think I'll say this to the group as well. The challenge here has been trying to find some subset of this stuff that can do something useful, like without the entire full-blown set. So like brainstorming around that, or things that we can do that are useful with some subset of it. Extra eyeballs and brain cells on that would be much appreciated.
Assuming like from the first patch that you could remove the MERMAP, and we would only have like only the simple stuff about changing the page allocator. Like how many patches would that roughly be?
Like 15 or something. And most of them are like silly. So like there's like one. No, there's like, okay, introducing this free type thing is like one really, really big annoying patch but it doesn't. It's not difficult. It's just like everywhere it says migrate type, you suddenly have to be like, is it still a migrate type or is it now a free type? And most of the time it's now a free type, and so you have to there's just a bunch of code that changes very slightly in annoying ways. But there's that. Then there's like one really interesting page allocator patch, which is fun. But the rest of it is just kind of like moving stuff around and preparing.
And the GFP unmap would not be for slab or anything like that. It's initially only for audio.
Yeah, and it would actually, the way I've done it right now is it's only for unmovable, but it would be trivial to extend it to work for other migrate types. But yeah, so it's only exactly what they need for Gesmo MFT. But yeah, and even actually extending it to slab should be fine. Also be easy, right?
So like the free type T, like because like recently we split off like from our core migrate types, we split off the isolated flag, and then we have like yet another flag. I keep forgetting what it is. But the free type T, would that cover these as well, or is it really just it's movable, unmovable? I think it's reclaimable, and then you would have yet another one which is unmapped.
Yeah. So the way I've done it right now, it just is. It literally is a struct, a packed struct into one word, but it's a struct with a migrate type and some flags. Probably then as a later patch that you'd want to like, is it still working? You'd want to start moving like the migrate isolate bit into the free type flags or something. Maybe actually this is a conversation best had over the code. I'm not sure.
Yeah, I'm just wondering like if the patch that you have is actually like more a hack that we hack it in, meaning like we have only this like unmapped memory, but like memory offlining would fail because we cannot isolate it, or if that is taken care of, that it's just another type.
Try to do it in a way where it's like not a hack, and it like
okay, good.
There's a good chance that you'll look at it and be like, oh no, you've messed that up. But
okay, but I mean like that's whole story of breaking it like into pieces, because then we can more sensibly review that part and identify problems.
It's supposed to be like properly integrated into the allocator, but it's only to the extent that I'm capable of doing that, right? Which is it's not that easy, but yeah. We'll see.
On this, like you're mentioning the planning,
yeah,
mentioning SMP protection. How much did you already work on this? Do you have that working? Do you have
yeah, we're still working on it. We're still rolling it out internally, but we have an implementation that works, we think. Yeah, I mean, we'll find out if it crashes if it crashes Google. Like, I mean, no, we've been running it in qualification for quite a while now, so I'm sure it's fine. But yeah, that's a tricky one, and it does increase that makes it quite a lot more expensive. We start to see like performance hits, like where we have to escalate to VPs if we're going to roll that out. But
there's a couple of
okay, yeah, cool. Yeah, that'll be
you also
great,
have patch set to the
Oh, nice. Okay, yeah. Cool, yeah. Sweet, yeah. Thanks, guys. Okay. Right, left? Yeah.
Okay, well, I think we're about ready for our next speaker. Okay, the floor is yours.
Thank you. So first, I apologize to the organizers for the time mishap. So thanks a lot for handling that. So the talk is about the new kernel CPU ID API and why are we actually proposing a new CPU ID API into the kernel and what is the progress. So why a new kernel CPU ID API? So the first problem is we have we have around 50 CPU ID leaves that various parts of the kernel actually query. And each call site actually does its own thing. And the first thing that a call site actually does is it has to query the processor of the maximum available CPU ID leaves to check if a CPU ID leaf is actually available on the CPU. And that's for each call site. And usually the standard level and the extended level. That's okay, not a big deal, but then we also have some CPU ID leaves which are only available on certain x86 vendors. So for example, the cache CPU ID leaf, that's CPU ID 2 and CPU ID 4, these are only available in Intel, Centaur, and Zoxon CPUs. There are some leaves that are only available on Intel CPUs, some leaves that are available only on transmit on legacy x86 vendors like Transmitter and Centaur and so on. And this leads actually to each call site having to manually query and see what vendor, and then depending on the vendor, should I query that CPU ID leaf or not. So this is the second custom thing that call sites actually do. So far, okay. Now, the third problem is that because the history of the x86 architecture, a lot of these CPU ID leaves have actually interdependencies. And some of them, like the kernel, say, okay, even if this leaf is available in the hardware, I need to make sure that 2 or other leaves are actually available. And some of that is actually handled by a dependency table in the kernel, and some of that is just at random call sites. So you will see call sites actually checking for a leaf and then checking for the availability of other leaves and then making a decision. And some of that is also exported by the x86 feature mechanism. And then we see that, okay, a certain x86 feature is available, the kernel declares it available to other subsystems and so on, only if a certain leaf is available and some certain global symbols and so on. For example, here for the TSC. And we began to see a pattern that all of the CPU ID call sites are actually a whole maze that nothing is organized. And all of that is also very old code. There is also situations, especially on legacy machines, where actually the state of the BIOS or the state of the CPU affects the available CPU ID. So, for example, on very old Intel machines, there was this CPU serial number, and if you actually enable it or disable it, you can change how the processor actually exports the CPU ID leaves. There are also on legacy Intel CPUs some MSR bits. If you clear them, you get more CPU ID leaves, and if you set them, you get less, and so on. Even on transmitter, so also legacy vendors, there are certain MSR bits, and if you enable them, then you get more CPU ID leaves, especially the EDX feature bits. So, and this is also handled again at call sites randomly. So each call site are just randomly querying all of that. And then the output of these CPU ID leaves are usually 4 registers, and there are a lot of bits. And then the call sites actually does a lot of ugly bit mangling to decide if a certain feature or of the hardware actually available and how to interpret that. And you can imagine there are hundreds of call sites in the kernel literally that are actually doing stuff like that. So it just query, for example, here CPU ID leaf 1, and then it does what looks from the outside extremely cryptic bitwise operations. And the good call sites, or maybe we can say the more modern call sites, actually can expose that bit view in their own unions and structures, in their own corners. But then we also have the problem that each corner is just doing its own thing. So we began tackling this work actually since some time, and I presented some talks. So the first thing we did, and I discussed that at previous talks, especially 2 years ago, was the x86 CPU ID database project. And I will not go into too much details here because I would like to focus on the new API. But just as a summary, what we have is that we have very large listings, like 950, literally, listings of all the feature bits on all the x86 vendors that we actually know and are public. And we have these detailed XML listings, and the project actually generate from that CSV bit field listings and C header files. The CSV bit listings are actually already generated, are already merged in the kernel. The header files are what we are integrating through the API. And you see here, maybe it's a little bit very small. This is like the CI pipeline for the CPU ID database project. And you see that we take the XMLs and then we generate the CSV and the headers, and then we validate that the headers actually compile and so on. So after this project and after we did the release and all of that, most of these CPU ID call sites are extremely old code paths in the x86 kernel. So I've dealt with code paths since Linux 0.1. I've dealt with code paths since then, but most of it like 20 years and maybe more, maybe less. And yeah, this is a very slow long-term project. So at the start of these projects, I had to actually list the call sites and then find which ones actually that need to be refactored before I even try to convert them to the new API, because just converting them is not the good way, and it was really hard anyway. So the first thing we did was CPU ID 2 and CPU ID 4. These are responsible for all the cache information, and I did a lot of refactoring of the code there, and this was already merged. And then the generated output from the CPU ID database project, the CSV files, the CPU ID database project has now like around 6 releases, and all new releases are, the CSV listings are merged already in the kernel under tools x86 KCPU ID. So then you can actually get the latest view of such files, plus a lot of bug fixes in the tool as well. After that, there was also bug fixes for the actual call sites of the CPU ID leaves. And yeah, so these things were, for example, miscalculations of the amount of caches and so on at each hierarchy. And it was also 15-year-old code, 16-year-old code. So it was not even merged to stable, because for 15 years, then probably no one hits it. But it shows you all the type of call sites we are dealing with. Then after that, there was also so a lot of the very ugly, very deep CPU ID call sites are now already merged, refactored in the kernel. So then the CPU ID headers themselves also needed to be refactored, and this is after all of this is already in line after a lot of discussions back and forth. This is the final view, And you see here just this is already now a standard in multiple places in the kernel. You see like the data structures at types.h, the exported API at api.h, and leaf types.h. This is not yet merged in the kernel. This is the auto-generated file from the CPU ID database, new API. There was also, as typical of these old code paths, a lot of circular dependencies, and I had to also untangle all of that to actually make this new API work. The headers work. Now, after all of this preparatory work was merged mainline, the next step was to actually introduce a centralized CPU ID model. And this is actually in the 5th iteration now. And what this CPU ID model does, most importantly, is that it ports this API to call sites from an external view. So it says that, okay, all call sites in the kernel should actually use this API. And this API looks actually so simple that it's almost undesigned, but I can tell you that this has been a lot of back and forth mainline to actually reach that stage. And what you see here is that for CPU ID leaves that are static, that you don't need, that are actually knowable at compile time, there are the first 3 APIs. And what you get out of that is the CPU ID leaf output. And then you don't actually have to deal with all the problems I showed regarding the CPU vendors, regarding if the CPU is actually, if that CPU is available, if that CPU ID leaf is available on the CPU, and other things. And if there are some certain CPU ID leaves that need dynamic querying, and that dynamic querying is basically that you ask the main that how many subleaves are available, and then dynamic number. So this needs a different API. And this is also after a lot of back and forth mainline. This is the API we have. Yeah, that came naturally, actually.
So how do we know who uses? So how the users know what to use?
According to your CPU ID leaf. So there are the CPU ID leads. So for example, CPU ID 0 or 1, that's already just static bit fields output. There are other CPU ID leaves where you actually have to query the CPU, and then it tells you how many CPU ID subleaves you have. And this is a dynamic, depends on runtime. And this is where you have to have actually to use the second leaf.
Why isn't this just a single API and then you figure it out underneath? Callers shouldn't have to know.
The callers know. So
Well, I mean, what if they get it wrong? I guess that's the question. Like, what if you use the top? Well, okay. What if you use the top one on the X8?
yes,
What is
actually, I added a lot of compile time checks, and if you use the wrong leaf, you will get compile time.
But if we know at compile time, so if we know enough to give you, can't we know enough just to bottom behavior instead? I guess that's it.
Yeah, because we do a lot of compile time things that actually we need. So there is a lot of machinery inside there to actually track that to the first CPU structures and so on. And that compile time and we can't, and this is actually, and we can't do that resolution if the information is at runtime. So there is a lot of trickery inside that actually that resolves directly to the per CPU place in memory to make it as just a single assembly instruction to execute. And for this to work, we had to separate it like that to the static part and the dynamic.
Important though. I mean, having it compile down to one instruction is great, but it's a super slow instruction, right? It's fully serializing. So, is there a goal? Like the goal, I'm saying the goal can't be performance to get it down to one instruction. So, what's the goal?
So the goal was to have a single static table of all the leaves. You can acquire them just with one interface, and you don't need to know. I think we should make it very simple for you.
I mean, yeah, the problem is that due to the compile time actually resolution we have, so far we have to make that separation. Whether we can mix it, we will see in the next slide.
But I think you're hearing a preference here. We would prefer, like, if we could give up on the compile time resolution, I think down super important. Just like superficially at the moment.
Yeah. So
I mean, if you cache everything in a single huge tree, you don't care about serializing anymore because it's in the kernel.
You're not accessing the instruction anymore. You're reading out of what we gathered on boot once. We want to remove actual CPU ID reads or using the CPU ID instruction in random driver code. Because the problem is right now, if we disable something in a CPU ID bit in the kernel, it's only software, but then the driver goes and reads CPU ID and says, hey, I have this bit, and you don't want to have it. So we want to, and then you get rid of all these stupid, find me bit 7 macros in the EAX register, which a lot of people got wrong in their drivers.
So
yeah, let me apologize. I think I was getting my wires crossed. I was thinking those were calling CPU ID,
no,
populating rather than yeah. My apologies. I'm getting backwards.
And also we're gonna use that for later also CPU defaulting, so we're gonna hide even more.
So
Be more in control.
So this is actually what I deal in the next slide. So what are the benefits actually of this API? So all of the returned structures from this APIs are already generated from the XML x86 CPID database project. That's the first thing. So all the data structures with the bit fields and so on, you get it out of the box. So all call sites don't need to define these structures or do any of these ugly bitwise operations. That's the first part. The second part is that we cache all of these CPU ID information per CPU, and we give you direct access to, in place of the information directly. The third thing is that we actually sanitize that for you, in the sense is if the CPU doesn't support it, or if the CPU vendor doesn't support it, if there is a dependency problem, like even if that CPU ID leaf actually exists, but what depends on does not exist, we just return you null. And then all the call sites are like in the patch series, we see call sites that have 10 lines of code, and they are actually collapsed to just one line. Just give me the data structure, check if it's null, and if it's null, okay, then we know that's not available. Then all that trickery is hidden from all call sites and drivers, and even normal. And this also finally allows us to provide a global view of the system CPU ID data. So there are cases where the kernel wants to actually mask certain stuff. We don't want all the corners of the kernel to actually just have direct access. And this is already now done out of the box. All of these actually CPU ID leaves are now converted. So it's actually most of the important leaves to the API. And the patch series has already all these code sites. The last version has all these code sites converted. The last stage is working with the x86 feature integration. And we also do a lot of compile time thing to instantaneously just give it the x86 feature and you get the value, and then we will. And yeah, that's all. Any quick questions?
Thanks for getting done through the slides quickly. So, I harassed you a little bit.
No.
Well, if there are no questions, no reason to leave it. Thank you so much. And that was our last scheduled talk. So thanks everybody for attending. Thanks for the great discussion, and see everybody in the rest of the conference.
The slide should be public, right? Yeah, of course. No, yeah. How do I? Also, that's my laptop. Gotta write my message on Zillow. Windows looks so much better. Look, I don't think
I'm using my laptop because I travel to China, so companies do not allow, so I have all the full encryption. I lost my computer, it's fine. I travel to China.
Me. Okay. Maybe that's my chance to do karaoke after all. All right, I think it's almost time to start. We have a few people coming. What's that? Oh, where is that? We might need him. I guess I can do the obligatory thanks. Thanks to our sponsors. This is a new session, especially NVIDIA. These guys are great. And with that out of the way, welcome to the first ever Nova GPU driver workshop. Danilo was supposed to give the Nova update, but unfortunately he could not make it. So I'll act as a backup as well as I can. So it's going to be a very, very short update because we want this to be a lively discussion. We have kind of a schedule, but please make it go off rails, you know, and let's have interesting discussions. So if I can make my stuff, okay. The main thing I think we want to share is how the project has grown this year, which was the first year it has been introduced. So the first lines of code in Nova Core have been introduced in 6.15, which was released in May this year at 387 lines of code. And today we are in master at a little bit above 10,000 and still growing. So what this gives us right now is that we have reached our first milestone, which is the GSP is booting and is running. So it puts us to the point where we can start actually doing interesting things. So this is happening for Ampere and Ada. And we also have patch series waiting to be merged for Turing, Hopper, Blackwell, which would cover all the GPU generations that we want to support right now. So the end goal of a driver, many people ask, but what do you want to do with that? So it's very simple. It's feature parity with OpenRM, which is right now the NVIDIA kernel driver that you have to build out of free. We want to have the same set of features, support the same things as it does. And things we'll be focusing generally and probably during this session are mostly vGPU, GPU virtualization, and where we're going with Nova DRM for compute and graphics. So what I'm showing here is the work done on Nova Core directly. So Nova DRM is still very very small, so I'm not mentioning that. But a lot of side work has also happened in the core Rust kernel crate because of Nova. So what I'm listing here is not entirely motivated by Nova, but has been influenced in some way by the development of Nova. So there have been contributions onto the PCI, aux bus, how you manipulate bit fields, define registers, manage interrupts, DMA, scatter gather tables. There's some work on the dummy allocator for from DRM. We need to there's a kind of some extraction work that we need to do before we can use it in Rust. Liud from Red Hat is working also a lot on DRM abstractions. We have firmware control and so on and so on. So it's actually much larger than just Nova Core because there's so much infrastructure to build. And big shout out to first Danilo for starting the project. Fortunately, he's not here, and also all the DRM and Rust for Linux communities who's I usually don't speak for NVIDIA. I'm speaking for NVIDIA right now, who has made us feel very, very welcome and like have guided us also to do that. But a lot of the work is also NVIDIA, Red Hat, Rust for Linux collaboration. So thanks to all the parties involved. And And with that, the topics for today. Let's already switch to the core of the matter. So I want to talk, I think John is speaking first. Did you have your slides? No slides. Okay. Yeah, this is better, by the way. I agree. So we're going to talk about firmware bindings, the GPU, user mod submission, because there are lots of unknown and, kind of random, not so random discussion about compute graphics, user space APIs that we want to build. So micro conference, you can intervene at any time if you take the Aperture Science companion cube over there. You just begin it, and I believe we're online. We have a couple of folks. Yeah, who are online. So people who are online, nobody complained they could not hear me, so I believe they can hear me. That's good. And yeah, please raise your hand if you want to if you want to intervene. And with that, yeah. I mean, I don't believe. Good. So okay, there you go, John.
I'm John Hubbard on the Nova team with Alex. And yeah, I would have had some slides maybe, but I was very casual about them. It's not sufficiently complex to require those. And so I brought an experimental laptop. It's a System 76 Linux thing. It's not so happy with my slide setup yet. So anyway, on the firmware, there's only a few things that I want to try to express because I think there's a few things that are not clear to everybody. First of all, when I say firmware, I'm talking about GPU firmware that it's from our point of view, it's sitting up in Linux firmware. You'll find it. I mean, a separate repository. You'll find it installed in user firmware or whatever. And so that directory is organized by GPU architecture. Sorry, is that not quite good enough? Yeah, so that the Linux firmware directory is organized by vendor, and then underneath that, under NVIDIA, you'll find entire architectures and the specific chips. And so that's where we get our firmware. And so we've been locked in place for the Nova project. We only support Turing and later. And what we've done is we've selected a set of firmware, or mainly I'm talking about GSP, but there's also little boot binaries and that sort of thing. And we've just locked on to 570.144. And so this gives us the effect of having a stable firmware interface. Questions or, okay. Oh, you all set? Okay. Yeah, so that one of the prerequisites we had for this project was, well, we can't be uploading different firmware that doesn't interface and is backward compatible with the kernel driver, and so that's a big deal. And so we've got this project going on to stabilize the GSP in particular. So GSP, please raise your hand if I'm saying words that make no sense to you, but the GSP is the biggest, most important piece of firmware. That's the one that we've been bringing up. So you need a stable interface to that. But then when we talk to our internal team, which is a lot of people. Oh yeah, go ahead.
If the GSP is stabilized, does that mean that when using, sorry, can you hear me well?
I can hear you. Go ahead.
So, currently when you use NVIDIA drivers, you often run into the issues where, I mean, not the novel ones, but the open and the proprietary ones, you often run into the issue where if you run a driver, that's not compatible with your installation of NVIDIA SMI or CUDA or whatsoever. It just complain about the driver version not being mismatched. Is that something that once you have a stable GSP interface, this issue can go away?
No. Any further questions? I will elaborate a little bit. The thing you're talking about is the user space kernel interface, whereas GSP is a kernel to firmware interface. Is that enough information, or should I go further? Okay.
Okay. Yeah. So, but I guess for Nova, you probably want the UAPI to be stable, or is that also something that?
Right. I'm not going to cover UAPI at the moment because that's the next level up of software. So
Okay.
at the moment, I'm really focusing on you are the kernel driver and you're looking at the firmware, which is the most important one is GSP. So let's talk about that for a moment. We can talk about the actually the last item on our screen there is about the user space API. So we'll talk about that a little later. Yes. Okay. Right. So where was I? Right. We want a stable GSP API, ABI even, because otherwise everything's just too hard. So our internal team said, well, that's a great idea. And what we have right now is not something we want to live with in the future. You know, it's 30 years of evolution. And so if you're going to make us stabilize this, we're going to insist on cleaning it up first and making ourselves happy, and we'll make you happy, and it's all very nice, but it will take time. And so while we are waiting, we simply locked on to 570.144, and we'll stay there until it makes sense to move to another version. And what I anticipate is that in 2026, we'll move to approximately one new version, maybe two. So what you can see is, you know, we're on 571.44 now. You'll see a number of months go by, and at some point, the firmware team, which is, you know, very tightly linked with the Nova team, is going to say, okay, you know, we've got something that you want, some new stuff that's going to help you. It'll simplify firmware, or it'll be the next level of, you know, whatever feature you're working on that will help you. And we'll say, okay, fine, we're going to lock onto that one. At that point, what you're going to see is we will drop support for 570.144, and we'll lock onto that next version. Now, next version, let's make a number. Let's say it's you know, version 600.12. We're not going to call it 600.12. We're going to call it 600 most likely, and that will actually, I'm skipping a step. Okay, take that tentatively. It'll probably be called something like 600, but without the minor version, because we expect that that'll be stable, and you'll be able to. It'll be stable for the things we care about, which is vGPU. I'm trying to express two things at once. I should split them up. The main idea is that we're gonna lock onto a new version probably sometime in 2026, but we're gonna drop support for the existing one. So again, we'll have the effect of having a stable ABI to the firmware. We can get away with this because the thing is not ready for real production use yet. Now, that allows some time for the firmware team to finish their work, and once they finish, then we'll be able to go to something like, you know, 600 and drop the minor version, and say that if we update it, we'll update it in place and we'll override it, and the next one, you know, will also be called 600. Or don't hold me to these details, but the main idea is that it'll be stable because some of this stuff is in flux. The main idea is that it'll be stable, and so we can do an overwrite and still get the same ABI. The version numbers and fooling around like that is a little bit TBD. The main idea I wanted to get across here is that 571.44 today, new version in 2026. We'll drop this one, we'll use the new one, and then eventually a stable ABI that we can upgrade in place without breaking us. Yes.
I was present last year when Danilo was talking about Nova in Plumbers, and one of the things he said was that you guys were going to experiment using traits to support multiple versions of the firmware at the same time.
That is so last week.
Jeez. Yeah. Okay. That's what I'm gonna say. What I was gonna say, because it seems like the plan has changed. If I understand.
Absolutely. Okay. Yes. Toss behind you.
I'm just going to speculate here. That plan's going to change again.
I think you'll see subtle. You saw me
I think
around with the
we're
version
about
number and all that.
6 to 8 months. We're going to be using traits and all that crap I wrote to reverse engineering. I will either generate it from something nice, but you're going to have to support two versions of firmware.
Oh, I am definitely open to the idea that we may have to support more than one version at a time. I shouldn't have made it sound like we won't ever do that. So yeah, we're open to that, but we're hoping to minimize how many versions are in.
Yeah, we don't want to be.
And we do want a stable interface into each one. For example, the team already now, the GSP team already has hard tests in place. In other words, fail the whole company if this breaks. They have tests in place today in R570 that if somebody changes the location of a struct field member or whatever, at the compiler level, we'll detect that and we'll fail out everything and you can't check in your code.
That's great. Like
It's fantastic
that's
stuff. And we're going to continue with that and more fiercely.
Yeah, I believe what's happening is that it's a change in release culture, right? Is in that before the kernel module and firmware were released in lockstep. Change the interface any way you want, it had absolutely no consequence. But now we are kind of warming up to the idea that, yeah, maybe we need to limit the breakage if we want to support an upstream driver. Can I?
So is there any plan longer term to maybe, I realize we have to support multiple firmware versions and those things, but to minimize the amount of firmware that we're having to ship in an MFS? Because, I mean, as a distro maintainer, like we just had to, with Fedora 43, increase the size of boot, and anybody who installed, a year ago, it's a 1 gig boot, and we can't have 3 kernels plus a rescue in there anymore.
Right. We're really very sensitive to that problem. In fact, that a lot of this has been driven by that concern. So yes, we also one thing, hold on, Dave, one thing that we've got cooking coming up soon. One of the things that's going to drive us to wanting to have a new firmware version is we've already got the idea of a simplified boot. I guess it's only tangentially related, but you can load, instead of loading 16 different little bootloaders and loader boots and boot loaders, instead of all that, you can just load a couple of files and then hit a register, and then the GSP itself will figure out what else it needs to pull from memory and it will boot itself up. And so there's going to be, as a side effect of that, there'll be less stuff on disk.
And I did experiment a few weeks ago for Nouveau, but I haven't actually patch I got sent out, but I don't know that would give distros the option of saying, look, I already know my Linux firmware is above a certain value, so you don't need to include the oldest one anymore because you know the newer one is going to be there. The only problem is kernel upstream can't do that because it has to assume there's no way to lockstep the kernel on the Linux firmware. But if you're building a distro and you're like, I know I put the Linux firmware out there already, and my kernel's never going to get booted on an old, then just turn that on, and it will just give you the 570 one, and so you won't have to carry 2 of them in the init ramfs. That's I sent the patch, but I think I forgot I sent it, and I haven't followed up as usual.
I don't have too much more than that, other than just tell me if I'm missing something that you care about in firmware, and I'll answer the question. But beyond that, that's the main thing I wanted to get across.
Yeah, I think one detail we could probably put in there is that, and it's kind of overlaps the UAPI, but is that if you're familiar with OpenRM, there's no real abstraction layer between the firmware, like the command sequences that sent to the firmware for controlling it are not abstracted from user space. Like it's all built as one in OpenRM, so they can get away with that. But for the kernel, that API is not stable yet either, and I think it may be stable work, but we don't want to expose that API to other parts of the kernel.
Absolutely.
It should all be contained in the Nova core driver. Look at OpenRM, you see it sending all these commands that are very specific to the version. We can't do that. We need to keep that in the Nova core project and then have the pieces in the kernel or APIs to abstract that out.
And to add to that, when Dave says Nova Core, you may recall we've split our driver into 2 pieces. So Nova Core is the lower one that talks to GSP, and Nova is the upper one if you're in DRM, compute graphics DRM, or there's a VFIO thing if you're in vGPU. So the stuff that is specific to the RM API and the GSP all stays in that lower layer, and we're not going to let it leak out. Our firmware team's actually quite excited about that too, because they don't want it going up either. So, other questions? Okay.
No, never going to get to that point. That's too simple. Doesn't do anything.
I mean, if we could get to a point where simple DRM, where you're using a small firmware and not having to load the real firmware until we've actually mounted our root file system in a default case, that would be handy.
We looked into it a few times, but for 3 scenarios, it just doesn't work. One that always comes up, you put your laptop lid closed and plugged in, and you don't. It never brings up the external monitors. Like you've got a docking station and there's 3 external monitors and nothing. It doesn't bring them all up properly. Prompt to do your own.
So the next 2 topics kind of could almost be combined. So we're going to be kind of casual about that. I mean, we can start with user mode submission, which, yeah, go ahead. Oh, go ahead. From Gary? Yeah, so Gary's asking, there's also an option to use UEFI frame buffer in early boot and only load the NVIDIA driver firmware later in the boot process.
Yeah, that's what.
That was the simple.
That's what the simple. Yeah, the simple question. Yeah, it's just not sufficient.
Okay, so apparently that has been tried and does not work, at least so far.
We're doing vGPU or?
We're going to go to, oh, I'm sorry, I skipped over. Yeah, so Zwang is up next. Although we've moved so quickly. Oh, he is here. Good. Yeah, go ahead.
Here's the mic, Gary.
Or you can join, okay, so you have to join the meeting. You need to join the meeting and then you can join the yeah. What's wrong with you? Just upload them. Yeah. Oh, this is like, okay, no. Yeah, I can. Well, maybe we can just go without slides.
Just the PDF for now, and I'll take care of the rest. And then we'll put your slides when you can. Yeah. Just
quick email, 10 seconds. Okay. Right now? Yeah. Can we just go without? Oh, yeah. Yeah, I can send it later. I think it's fine. I think. Okay. Yeah. Okay. Oh my God, sorry. I really didn't know, like I have to upload it first. I mean, well, sorry for that, but well, yeah, I mean, I'm Zhi Wang, so I'm mostly the guy who work on the vGPU in NVIDIA. So, I mean, if you, you know, see my presentation in the QVM forum, I think, well, you will know, like, you know, how basically like NVIDIA vGPU works. Sorry. Yeah, sure, please. Yeah, so you will basically know like how NVIDIA vGPU works and like what kind of resources need, and also like all the other kind of resource like you know, command channels and the frame buffer, all the stuff, yeah, need to be assembled before like you create a vGPU. Yeah. So for us, we have already published like 2 RFC already. Yeah, first RFC is based on the NVKM, the other one is based on the Nova Core. Yeah. And we were like planning to move it faster, I mean, after these 2 RFC. So we have a plan like for 2 or 3 stages, 2 stages and 3 stages actually. So the first one is like, as you know, like the vGPU, they need, you know, a very special configuration for the GSP, mostly larger heap size, and also like for ADIs need the scriber your image to be around before like everything work, right? So, and thanks for other guys' work actually. So many of the dependencies has already been like checked in, mostly in Nova Core part. So that gives us opportunity, like we could try to introduce these very minimum basic blocks actually to the Nova Core. So yeah, we have actually 2 dependencies on the RESTful Linux. So one is like we need to access the PCI configuration space, you know, to read all these SRV registers in the SRV caps actually, and to put that in the GSP initialization data structure. And I have already posted some patches, and thanks so much for Alex's review. I would just say thank you so much. And also Alice and Alex, I would just say thank you so much. And there are, and also Danilo, yeah. So it's like version 6, I think, yeah. But I think, well, we will figure out a solution to move on from there, yeah. And the other part is like we need some kind of bindings to be exported for getting the total numbers of the virtue functions. Yeah, with those two, I think we will make for the stage 1. And stage 2, we get a little bit more things to do actually. So mostly like we need to bootstrap the vGPU. Bootstrap vGPU actually, we need all these very fundamental components like in the core driver, like allocating memory and allocating, all kind of things like, you have to be able to manage the bar mapping, which you got dependencies on like managing memories and range allocators and, interrupt, and also refinement for the GSPQ, like, yeah, those things mostly like in the Nova core. But we also have one dependency is actually on the firmware control, which is like, upload the vGPU type blobs. Yeah. And also like we might explore more options like for, how to leverage firmware control more in the future. Yeah. And then the stage 3 would be like, we could really enable VF, which Peter Koberg is working on the patches, like to enabling the virtual functions from the PCI level framework, yeah, and to boot up the VMs. So that's basically the current plan for how to move on from these two RFCs. Here I would just say thank you so much for Rust for Linux guys, for the help and for the review. And also thank you so much for other guys like Nova Core and Nova guys, for our kind of like patch review effort to make this moving on. Yeah, thank you so much. Yeah, basically that's, the plan for the next, I would just say. So any comments for these or questions? Yeah. I'm so sorry. Like
I've got a question, but it's just I'm going to repeat a question went on the mailing list, and I'm going to ask so you can say it on count. So one of the things that was brought up recently by Christian on the mailing list is like when I was discussing, like maybe I'm actually not sure this was on the mailing list. I can't remember. I was having a discussion with Christian Koenig about the split driver architecture of Nova Core and Nova DRM and Nova Core and VFIO. And one of the things he brought up that might be a fun problem was something to do with whether we need DMA buff in the VFIO driver and whether that's something that we're going to need in the future. We may not need it now, and whether we have looked into it. And I wasn't really sure where we were, because he brought that up as something when they had considered something like this, but their split was a dumber split than this one. They hadn't really figured out what they wanted to do yet, but they have their separate GIM VFIO driver and they have their DG4s. Yeah. And I was like, oh, we could do a similar split, but then he brought up DMA buff and I was a bit like, I don't really know what needs to happen there. So maybe you can.
Yeah, I think, well, for, yeah, go ahead. Okay, good. Yeah, I mean, in this architecture, so mostly like, if you think about the DMA buff, right? So mostly you use the DM buff. I mean, well, mostly from the VFIO part, I would just say VFIO actually have an like very additional like IO tools, like you can actually query the your display surface format, all these kind of things, and then after that, actually you can generate kind of like object, so that you can accept. Means like you can actually show the virtual function, the VM's screen. But it actually provides two kind of like type. One is like, you can actually just directly get some kind of, frame buffer like address where you can do the memory map actually. And that was like supported in the QEMU already. And the other part is like, you can actually export it as a DM buff object. So for that part, it's mostly like, EGL actually have an extension, like you can actually generate a EGL image from a DMA buff, and then you get a EGL image, and then later you can turn it into, textures, all the stuff, and then you can, do the compositing in the Windows system, do some fancy things. But for NVIDIA, actually, we support this, the first one, which means like we don't actually need to do the DMA buff things. Because the second one, I think, well, it depends on the use case and, the customer requirement, all these kind of things. So besides that, I don't think we have any more requirement for the DMA buff in the NOAA core, actually. I think I also explained that in the island list. Yeah.
That's what I just, one thing when we do put something upstream, all of the customer requirements and things,
yeah,
can often get like, oh, I want to try this out, and why doesn't it work? DMA buff. So I'll just make sure we definitely dug into it with sufficient that if someone, we know it's either going to work or not work if someone does try to add it later.
Yeah. Okay, so any more questions? So, is there online questions? Okay.
Can we write the VFIO bit in Rust yet? Can we write the VFIO bit in Rust yet?
I will let question yeah, but not I'm not the guy, so sorry. Yeah. Okay. So thank you so much, guys. Thank you, and hopefully you enjoy the whole LPC journey. Yeah, thank you.
Okay, so yeah, I guess the next topic is our user mode command submission. Let's see. Let me read it out from David. Regarding UEFI GB. Oh, okay. Okay. Yeah, so the next topic is user mode command submission, which I said is kind of blurred in a little bit with user space API. But Alex and I were claiming that we can just say those words out loud, and then Dave will be triggered, and the rest of the conversation will take an hour or two. but really, thanks, Dave, yesterday or the day before for walking me through the latest version of some of the difficulties about setting up for user mode command submission to GPUs. So just I'll spend 30 seconds giving a little background. The NVIDIA driver stack for both compute, for CUDA, and for graphics has always had a user mode command submission model. And that means that we simply create an area in memory accessible to both the GPU and the CPU. And we, the user space program writes in commands, and the GPU reads that memory and runs. And so that's really as fast as you can run. And so we're, obviously we don't want to lose performance and change to something else. And that something else would be a kernel mode submission model where instead of doing it that way, you still set up a command buffer somewhere, but then you have to make IO control calls to say, it's all ready, start running. Oh, are you done running? Okay, now that you're done running, I can release things. The fundamental difference, I don't know if I'm making it through, the fundamental difference between these is that there's a trade-off here. So if you use the user mode command submission, you can't tolerate oversubscribing your video memory. So that wasn't immediately apparent to me. But then if you imagine that you've got two processes running, and each of which wants to use more than half of your video memory, and that's how the kernel mode submission model works today. The key is, though, that it uses a series of kernel calls in order to coordinate that. So if process A says, okay, I've set up this memory, it's resident, you can now run your program, and then I get notifications when you're done. And so then I can, once you're done, that memory is available for somebody else who may be oversubscribed on video memory. And so things can progress. And that's how the Linux kernel's graphics, DRM graphics thing works today. So that gives you oversubscription at the cost of having kernel mode command submission, which requires transitions between kernel and user space and is therefore slower. The NVIDIA model, on the other hand, does not support oversubscription. Now, the internal NVIDIA folks on graphics side would love to support oversubscription. On the CUDA side, we already do, but we have a different, we don't have the same latency sensitivity, so we can handle page faults and it all works fine. The graphics side cannot tolerate page faults because it's too latency sensitive. So the graphics guys have always said, well, we wish we had oversubscription. It's something we really want. But we can't do it because we're not using any sort of coordination mechanism. So we're just saying, allocate the memory, run the program. You know the objects are there because you just allocated them, and you know nobody's going to make them go away because oversubscription is not supported. So that, as I understand it, is the fundamental set of limitations we have. And what we want is we want it all. We want to have user mode command submission with Nova, and yet we want it to be coordinated so that things work. It's an unsolved problem yet. And at this point, I expect we can trigger Dave to. Oh, is there? Hold on. Okay, so the question is, I believe CUDA unified memory is also not available for some consumer-facing cards. That's not correct. It's available everywhere. End of story.
Except on Windows.
I'm sorry, what?
Except on Windows.
I don't even, when you say Windows, it doesn't even go in my head, but
I thought I finished triggering John.
I'm so sorry.
Yeah, that's the thing. Yeah, I would say it's not solved because I think we have got something in for AMD recently, but I'm not across how they solved it. I have to go and check.
Did they? What is it? A posting or is it?
No, there's a thing called user queue for graphics 12 that they've done. They've set it up, but I don't know how they've done it in terms of whether they have to fall back to the kernel a lot. And that's why I haven't got the figuring the detail. I need to get the graphics card the next few weeks.
I mean, where is it, like a posting to the list or something, or is it in the kernel already?
Sure, it's probably merged because a lot of work was in Mesa to use it and stuff. But I don't think it's the default path for it. It's only like one card, the latest couple of cards that need it, that use it. So yeah, there's something like, as in we're a lot further along the path of solving it than we were last year. But yeah, there's still some unknowns, I think. But Christian has been doing quite a lot of work trying to figure out what. But I did ask them, how did you solve the 51% VRAM problem? And they're like, yeah, we solved it. I'm like, but I think you could do certain things, but I don't know if you need firmware. That's the level of detail I'm not across at the moment. It's like whether they've done it by having firmware help out with this, or whether there's some assist needed from the firmware. The traditional way we've done this, but I don't know if the AMD KFD driver has done this already. That was one of the barriers for getting AMD KFD merged was that they needed to do proper oversubscription, that we wouldn't let them merge it with pinned memory allocations. So one of the biggest projects they did 4 or 5 years or whatever, 6 years, probably 10 years ago now, I don't know, was to at least work out a model for their compute driver that allowed video memory. And the way they did that stage was they would map the page into the process, but if the other process took your memory, it would invalidate your page. So you would no longer. So the next time you went to hit the register, you'd either get you could ask, or you could just get you'd get sig.
So it was a page faulting model.
Yeah, it was, but in user space, it was like you just unmapped the doorbell, and then when you'd unmap the doorbell for a while, and then
just page fault for the doorbell only.
Yeah, only for the doorbell. But so when process B went to do its next user space command submission, it gets sig bus, and you'd catch sig bus.
Oh.
Or you'd use, there's nicer ways of doing it, but essentially that's the essential model. Then it would go, can I go to the kernel and go remap my page? And the kernel would then leave it a while so the other guy could make forward progress. There was enough that we won't, so you would guarantee you wouldn't live lock in that both processes were just kicking the other one out constantly and no one was moving forward. You could put in enough of a scheduling, well, let process A move forward, and then process B will get its page back and kick process A page out. And they'll just constantly bounce between the two of them, kicking their pages out. But to me, that's not the most latency fun thing to have to do either. So, but again, this isn't a common case. This isn't something you should be running into while you're playing your game or running your cat app, or but it's something that's like overcommit on swap. It's like you just need to have it so that you don't fall off a horrendous cliff.
One of my favorite cases for this has been you've got two screens, each of which uses most of video memory, but you minimize one and then look at the other, and that actually sounds like a reasonable case.
Yeah, and it's if you're running a cat app with two heads and they're both running at full, or two games on the same thing, it's even more fun. So it's like, but yeah, you just don't want to run into, like, one of the problems we have with the graphics driver in the field, like when we went to compositing, like before compositing, and when your graphics card was just running one game and Xorg, and
on Windows,
even on, it wouldn't run a game on Linux, but it was running a cat app, say. It could use all the memory because there was no need for anything else. There was no dynamic really outside of the one app. But when we moved to composited desktops, the compositor was constantly reusing the frames and wanted to add new frames. And then you would have a cat app, and a cat app would just start to use more memory, use more memory, use more memory. And then the compositor would put one frame into system memory because there was no VRAM left, and your performance would just go. And that was one of the reasons we pushed strongly against that model in our drivers, because it was like the cliffs were just horrendous when you didn't hit them for a while. You just put more RAM. That'd be, buy a bigger GPU, you were good. But it was like a bad cliff.
I see you seem concerned about latency if we have page fault. But if you're oversubscribed anyway, this means you have to migrate pages back to VRAM. So are you that worried about a page fault in that case?
Probably not. Like, probably if you're not, you shouldn't be hitting it all the time. So probably it's fine to just take. I don't like hitting SIGBOS, but that's just an off way to get that.
And for the record, I think this idea of basically unmapping the channel from the user space process is how NV1 managed context switch between channels, if I remember correctly. or was it NV3? I don't know. Yeah.
It's kind of like a poor man's page faulting in a way, but but we can't, as you all pointed out earlier, we can't do a page faulting approach because not all the units of the NVIDIA GPUs will support replayable page faults. So that's kind of a dead end. So I guess we're stuck with, my gosh, signal handlers.
Yeah, well, I'm hoping we can avoid the signal handler.
Yeah. Yeah, I'm not seeing the question up here. Oh, is that Bill Beer?
Hey,
yeah. Okay. Yeah, go ahead.
The question was, with respect to video memory management, isn't C groups a better way to sort of deal with the fact that you have two competing applications trying to allocate memory? It's better to do the service level objectives ahead of time so that you know how much each can access, as opposed to trying to fairly balance or distribute memory.
Go ahead, Dave.
Yeah, I gave a talk 2 days ago on precisely that topic for how DRM and C groups are going to go, and that's fine if you're in a static partitioning world, or you know in advance. But for most, at least desktop applications, or it's like you're just running on the fly and you don't really get to do C group setup at that level. But yeah, for cases where you care about that, the C group work is ongoing to do that. It's not upstream yet, but we're working on it because currently there's no real DRM and C group integration.
Well, and the C group thing, like you said, because it's static, it doesn't address the oversubscription at all.
Yeah, and that's the eviction of memory between the C groups is the open problem we've suffered from.
Right.
I think the thing is that if you really want to build a oversubscription in terms of the video memory stuff, right? Basically, let the kernel modules know what's before the buffer gets launched, what's all the resources and pipeline that. Right? That's already solved the problem. So I don't think there's any.
Okay, so if I understand correctly, Neil, you're saying so if you have, say, two processes, each of which uses 60% of video memory, you're saying each one describes what it needs.
It's not even at that level, right? It's like I want to launch a buffer, right? It's all at a buffer level, right? I want to launch a buffer, and then what's the dependency of this buffer?
Well, first you have to allocate the buffer. That's the problem.
The buffer will be allocated, right? So you have to describe what's buffers, right? And
well, wait. let me stop you there, because the buffer won't be allocated unless you kick out somebody else's buffer that the SM is running on and depends on. So that's the core of the problem there.
Right. So that's you want to allocate the buffer, right? So you want to say this is all the commands I need to execute, right? Then the dependency, you describe the dependency of those buffers, and then give it to the kernel modules, and that kernel module to handle all those paging. Then he'll page out all the whatever that's based on his policy to page out all those things. That is not running, right? Then you page in the application running right now.
So when you page things out, that other application may have been using them. So, but we can't tolerate page faults.
Yes, but yes, other application might be using it, right? So that's why, because the kernel mode is doing the submission.
But we want a user mode submission.
Yeah, that's what I'm saying. Is the kernel mode is doing.
Right. So for kernel mode, it's a solved problem and it's up and running upstream. But that's not what we want. We want everything. We want it to be solved, but with user mode submission as well.
Yeah, for the user mode submissions, then you need to just coordinate where actually the paging.
Yes, and that's what we're dancing around, is trying to figure out decent ways to do that. And Dave is claiming that we can somehow avoid the signal handler, even though we. I like that. I mean, it would be nice to avoid a signal handler, because I've worked with those, and they're actually kind of woven evil.
Right, and also we care about latency, right? So we must recruit applications.
Right. Although for the oversubscription case, latency is important while the application A is running or application B is running, but while they're contending, I think you've got a little bit more room on latency. Doesn't that make sense? Right. For the forward progress contention, you've got a little bit more grace period for latency, because you've got two things that are contending. And so they've got to be allowed a little bit of time to work things out. Once the contention is more or less resolved, then, if you've maximized application B, it needs to really run the way it was running, with no pauses.
So, if I understand correctly, it doesn't solve the problem of one application. If you have
in that case, you're just asking for a slow application,
right?
Yeah,
but even there, you cannot solve that by using page faults, I guess, right? Because
because
your ability to progress, right? Your ability to progress depends on knowing what you need for the next batch of work. And not all the stuff you have, of course. So I guess this is a limit of what we can achieve, right?
One thing that we do now so we used to do what you said in that sort of, we had a command buffer and we would keep all of the dependencies of that command buffer tracked, and the user space driver would then just build this tree of buffers, and we would give the kernel all of those buffers. What we've moved to now in nearly every driver, and perfect, but it seems it's better, is that you create a VM level and you connect all the BOs to the VM in the kernel, and then you just say, put this VM back in memory, make it all resident, every buffer in this VM. It's not as fine grained, and it can fall off different cliffs, but it's just less CPU overhead for everything. It's and the hardware supports it. And we don't need to do the dependency tracking anymore. It's just you have a VM, and the question is, can you just put all of these buffers back into memory somewhere for the VM?
I mean, what would you, that current model that you described, it has a lot fewer kernel transitions, right?
It does, but it allows you to do a lot more oversubscription on yourself, because you can then decide which more control. But there's actually now APIs with Vulkan that you can't know every buffer you're going to use. The dependency is no longer there, because you can actually pass out a 64-bit a device address back up to the user, and the user can just pass it back into the shader somewhere random. So there's no way now anymore that model works. You have to tell the kernel, I need the whole VM. Everything has to be mapped in. So
I'm intrigued with that direction, because it sounds like it's hard to describe it as user mode or kernel mode. It sounds like a little bit of kernel mode help, and then
well, the user space defines the virtual memory address space and what physical buffers are mapped into it, but then it asks the kernel to make that real every time it needs to submit.
Right, but once that happens, it sounds like you're running still with, you're writing your your commands to the command buffer in memory, and you don't have any further IO controls.
Yeah, you shouldn't need to ever move it again until someone else kicks something out and invalidates it.
Right.
Until another process runs and
See, that's pretty interesting because it sounds like a perfect hybrid.
Yeah.
It sounds very close to our user.
Yeah, so that's the thing. Yeah,
with kernel help.
Yeah, with this is like you in the ideal steady state of this, you would do the ioctl to say put all my buffers in residence and then just use a space command submit forever. It's only in that state of when the other process kicks something out of video RAM. Something invalidates your virtual memory to physical memory mapping. Something kicks something out of video RAM and you no longer have that address in physical. Gone. You have to re-put it back together later. So
Yeah, this sounds like a fantastic direction. There's one thing that I would add, and that is that that's going to work for graphics. Using the same driver stack for CUDA, we'll also need to, we might need to add a model in there because CUDA is going to want a low CUDA launch latency. Some of these customers, it's amazing. You build something and then people insist on using it. And so they've gone out there and they're using CUDA. It's very irritating. And and they're generating these tiny little programs that all have to launch very quickly, as on the order of a microsecond, and then they just throw them at this. And they're happy doing this. So CUDA has spent years and years making sure that they have a low latency for starting up a CUDA kernel. Think of it as a graphics shader, and lots of them in quick succession. But I think that can coexist with what you've described.
yeah, it shouldn't be that big enough. You still have to, the operations that CUDA has to do are the same operate. You still have to allocate physical memory. You still have to allocate virtual memory.
Right.
You have to
Just do it
bind the
up front.
physical to the virtual, and that all has to happen before you submit the first piece of work. So
Yeah, and then it just goes as fast as
and you can we batch a bunch of those right now with VM bind, and I think Intel have done something that makes it more compute friendly to their VM bind. So I think it's not it should be pretty simple to do.
Yeah, I really like this because it sounds like what we're zeroing in on is it doesn't matter what you call it. You could call it either one. Maybe you call it user mode submission with a little kernel help or vice versa. But whatever you have to tell your management teams to make them feel comfortable. But it sounds like it is a solution, really.
Yeah, it makes it easier, but you still have that fundamental problem when you submit work. You have to have the memory set up, and if it's not set up, you have to know. Solve.
Yes, I mean the initial, CUDA initialization is not a quick process already, so I don't see a problem yet. I'm sure somebody will point out something, but all this stuff is already upstream and working.
Yeah, it's what Nouveau does with GPU VM stuff.
Okay, so maybe this is less of a landmine than I thought. Maybe we'll start trying it out.
Yeah, I think we need to get to the point where we can just do user space command submission and see what the hell breaks. See where it falls over and stress test it a bit.
Right. Okay. Well, that was surprisingly easy, and I'm not sure what to think about this now.
I have ideas of optional, sort of like you could do it in a way that where you would try to write to the page. If it's not there, you could then submit a kernel ioctl and pass it the page, and just have the kernel assist the next one.
Doorbell page?
Then the kernel would, at least you have an atomic operation of mapping the doorbell page and submitting the work to it that first time again, and then it may stay there forever. But somebody said, that you may need to do one kernel call at that point, and that'll be enough, but you still need the atomicity, I can't say that word. You still need atomic operation of both move my memory and submit at least some work, and so it'd be like a kernel assisted start for some of them. But I'm vague on, it's very hand wavy. It's just
And that one scares me because it sounds like a slow. I mean, the CUDA launch latency gets.
But by default it would be user submission, but only when you needed to, you would do it through the kernel. It would be like an assistant.
And how do we decide you need to?
When you can't do it through user space because the page isn't there because you've been kicked.
I see. I see.
You would try to reduce those latencies by batching the operations to the kernel or not. It's hand wavy because I'm not sure what we're capable of doing.
And how do we decide when to unmap that doorbell?
The other guy, we don't get to decide that. The other process does it for us when we move memory.
And I guess the other process, when it goes into the oversubscription case, then it decides to unmap.
Yeah, when your VM gets invalidated by somebody else moving your memory around behind your back, you have to then unmap that page.
instead of the signal handler to tell them that, hey, you need to call dioctal, you just unevict all the pages in the page fault handler and then transparently handle it?
Actually, yes. Yeah, that probably would work. Yeah, I think we've done that.
We're talking about doorbell.
Because that's actually how we do migration. So with like if you have a buffer object and you've mapped it to user space and it's in VRAM and somebody moves it, we just invalidate all the pages, and the next time we get a page fault, we just page fault back in the system memory pages in the same place. So yeah, no, I think that would be fine without having to hit the sig bus. We just deal with it.
Are these all CPU page faults we're talking about?
Yeah, CPU page faults.
Yeah, so we're safe.
Yeah, that would be probably fine.
Yeah, it beats a signal handler.
Everything beats a signal handler.
Yeah, and there'd be no ioctal, so you could call it user mode.
Yes. Thank you. That's very helpful. I guess if there's no big other questions, we can move on to chatting about the user space API.
Yeah, we're moving very fast, actually.
Yeah.
That's getting me worried.
Yeah. Again, feel free to interrupt with stuff that's on your mind because we're ahead of schedules.
I believe one topic we skipped at the beginning is the one of bindings generation.
Oh yeah, we
Do we want to
can
share
cover
some
bindings
stuff about
generation. Yeah.
What can we share about that?
Well, let me think. Right. So yeah, on the bindings generation front, we've had discussions with all of you on the Rust side about, well, for example, can we generate these bindings directly as part of the build process as opposed to having to run bindgen? And I actually I keep forgetting what the preference is. Someone remind me what's the way of truth? Isn't it to not use bindgen? I think is that the preference?
So bindgen's job is to translate C structs into Rust structs, as far as I'm aware, and functions. None of what we're describing is C structs. They happen to be represented as C structs in the NV driver, OpenRM driver, and they happen to be represented as C structs that use every imaginable way you could ever represent a C struct. But they are not C structs. They are memory alloc space, like they are RPC messages. They are memory address. Just because you're representing them as C structs doesn't mean we should use bindgen on them to translate them into something. Also, they are not stable C structs. So if you're going to bindgen them, you have to then append a version number to each and every one. And I know that's probably possible, but it starts getting messier as you keep going down the depths of it. Like we run into if that C struct is 570 stable and there's another one that's 580 stable, and you have to hide that stuff into a very specific piece of code. It just starts getting higher. Now, I'm not saying what I did was a good idea. So I wrote something that was, I don't even remember the name of it now, like LLVM Clang. I used Clang RS to parse all of the NVIDIA OpenRM header files in the whole driver and pull all the structs out, exactly what bindgen pretty much probably does, but then generate a memory map thing that you could just fill in the memory map thing, and then it was all specific to each firmware, and we could hide it away in the depths of the firmware and put a trait that calls all of it. It was really nice hidden. But the thing is, those structs, you're generating them from obviously an internal database or something else.
Right, and we could generate the Rust directly. And,
Yeah.
and I remember you guys were telling me, yeah, there's extra information that we can generate along with it, like array sizes and all those goodies.
And the other reason I had against using bindgen was the first attempt at using bindgen was doing it against the Nouveau headers that are in the kernel tree. But the only reason the Nouveau headers exist in the kernel tree is because the Nouveau maintainer hand picks them out of the NVRM headers. So then it was like, well, if we're going to base them off the Nouveau headers, someone has to keep updating the Nouveau headers for every firmware we move to, even though that's not a part of this project. It's like, so it was a dependency on another project that I don't want to have.
Right.
It's like, yeah, if you could do this from your tree, if we could bindgen them from the OpenRM tree,
Yeah,
but
and we could.
That's what we're doing, yeah. And I think that's clean enough-ish, but I'm still like,
Yeah. Yeah. Today we are doing the bindgen from, Alistair wrote this stuff from the RM, but we are definitely free to generate the Rust directly.
So I would like to ask for a bit more context on what you mean by bindings. For what are you using those?
Or what are those in the first
okay.
place?
Yeah. For example, suppose you want to make an RPC call to the GSP firmware. We have header files for that explain how to do it. But we also have information about, exactly what goes in those messages. For example, you might have a struct and it has an array and there's an array length. All that stuff is known by the GSP. And so at build time, it's perfectly possible for us to use our interface definition language to generate Rust instead of generating headers. So we have that option. We can do it. Yeah.
Yeah, I guess I did a lot of the bind gen stuff initially, and it was very much done as a stopgap measure to get us to sort of have progress moving forward. Like all good stopgap measures, it'll probably still be here in 10 years. Hopefully not, though. My intent is not to have it here in 10 years. But yeah, we basically just hand pick the bindings we need from OpenRM at the moment and run bind gen against that just to sort of get us going. But I think the long-term direction is definitely we need to generate them for our internal databases, because I agree with everything you said, Dave, in terms of them not being safe struct. They're not C structs. They're not safe for the way they serialize. I have questions about how it's done in the firmware side too, but that's the right answer, I think.
Just for that case of what are they representing there, that's also why I don't like using bindgen for them. They are not representing an interface to a C thing. They're not representing like a C part of the kernel you're calling into. They are just a memory mapped thing that you're going to fill in using these structs. So there's no you literally have, when you go to make the RPC message, it's like, here's a pointer and this struct, fill it in this memory with that struct. But you're not talking to a piece of C. Like I consider bindgen to represent that. I've got C code and I've got Rust code and I want to talk between them. This isn't that. This has got Rust code and it's talking to firmware and just happens to use C as a representation of the memory.
Well, the C code is running on the firmware side, right? So your RPC is basically remote procedure call. So, you're making a call to something. I kind of see your point, but it is a command response kind of thing. Yeah. Can I ask another? So I guess I was wondering. So we do have this abstraction right now, thanks to Alex and others who worked on that, like where we don't let stuff inside Nova to directly use the firmware bindings. And I'm wondering if what we have right now is enough, and we don't need the version fields thing that Dave, you had, I think, come up with. I think that depends on out of tree patches as well for the versioning.
Yeah, I think it is possible to generate this in a way that's encapsulated in a. But until you get to the second firmware and you prove it to me, I'm not trusting anything you've done, because it's so easy to leak this stuff out. If you even look at Nouveau, what Ben did, or architecting it, everything into pointers and putting them into directories and hiding it, and it's horrendous. And if you look at what I did when I wrote the Nova Core demonstration branch, I encapsulated everything at a trait level, and all GSP operations are hidden, and there's just no way it leaks out. And then when it does leak out, I was like, yeah, Rust catches it. So it's like, okay, this is good. You can't bypass it, but it's very obvious that you've done it. And I'd like to make sure that, if we do something like this, it's very obvious when it does leak out, because enums don't even stay the same. It's really that hit Nouveau really badly. It was like, well, we can trust this enum's going to stay in the same order, and then somebody went and inserted a new one in the middle of it, and it's like, you need to rearchitect your whole driver. And if you've exposed it to user space, now you have to have a mapping table between the old one and the new one. It's like, yeah, so it's.
I would say that even if you are talking to a piece of C code or whatever it runs, right, firmware or whatever, bindgen is your last resort. If you have a better thing, use it, because then you can encode more things. If you have your own internal database with more information about whatever it is, constant functions, you want to use bindgen when you don't have other recurs, right? At least not just because of the lack of the C semantics, the lack of what you can encode in C. It's not just that. It's also the fact that bindgen may have a bug or whatever. So if you have another way, a simpler way to encode other things, your bindings or it's much better. The same way the Windows or Microsoft has this IDL as well, where they encode the interfaces for several languages, and they can put it in the high level. In the top one, they can put much more information, and then they use it in different languages, right? So Bindgen is like the low, like your last resort, I would say. Okay.
So just a very short thing on that. If you want like new types for some pointers which are only available on in the firmware, so like the firmware gives you a pointer back and then you have to put it like somewhere else. For example, you might want to use a new type for that, and then you can specify that in the Rust part of those bindings, and that you can't do in C.
I was just, I guess, going to go back to Dave's other point in terms of the versioning as well, and keeping things compatible between versions. I think, this is how I probably end up in a pub buying Dave a beer next year. But by saying, trust us, we have those internal processes that John's sort of talking about there in terms of when people change those bindings, we break the company, so to speak. And I think that should be the long-term direction. We shouldn't be trying to replicate that logic in the Linux kernel or in our build processes or in our source code structure within Nova. That just makes work for Nova that we're also already doing internally. And if I'm wrong and we get to that second firmware version and we need to now version the structs because we messed up and missed it, then I guess I get to buy you a beer next year.
So yeah, another thing I think of note when we run bindgen on these C headers, there is a lot that is lost in translation between the thin, the original, IDL, and C, and we are getting like these bindings where unsigned integers are like magic numbers are represented as negative numbers because anomalies or things that should be enums are just a bunch of defines. And so right now in Nova we have this layer that is in fw.rs where we try to unsee the bindings generated by bindgen and expose a decent Rust interface. We had some back and forth with Alistair on that, and it's something that we could probably reduce dramatically if we had the ability to produce Rust directly from the IDE.
Yeah, I think we're all in pretty violent agreement that bindgen is not the long-term direction here. The background was, of course, we need time to write that internal tool, and so that's kind of why I grabbed bindgen instead of figuring out Dave's stuff and maintaining another tool that was not written for that. If we did it internally, then if we unblocked ourselves.
Another thing of note with the IDL, it's very well documented. We could extract this documentation and include it in the binding. That's also one of the goals I think of Nova, is that it's well documented and it's easy to.
Yeah, I'd like to see the stuff that's in OpenRMC header files be the exact same stuff in the Nova header files, but in Rust, like all that documentation that comes with all of those control commands, all those we need. But yeah, OpenRM, all the controls, maybe not the low level RPC, but the higher level control commands you send through the RPCs, nearly all of them have comments, and it's not complete, but there's quite a lot of information in there.
I don't believe bindgen has the ability to extract documentation from the CE. Yeah, that's.
So it does, but the problem is that we will need to convert to Markdown or have the Markdown on the other side. It's a mess, and it's apart from what everybody else says. It's even more things that when you think about it, it's way more things that you can do when you have another representation. Like you can do the safety, of course. You can use the enums. You can use the write tests. Maybe you can all kinds of things you can do. Bindgen is really and what you mentioned, Alex, is what I was trying to say with the bugs, because some of the things you mentioned for me are kind of in some cases are bugs and in some cases are intentional or intentional, but yeah, bindgen is not.
Was one of the reasons I wrote the horror show I wrote was because that was the only way. I also, like, you still have to do a whole of pointer dances and unsafe stuff. Then a lot, you can cover it over, but by doing it with like a mmap representation, it was like all I'm doing is filling in an array. There's no safety problems in any of that code. It's horrible, but very safe.
To our defense, a bunch of that can be avoided by using init threads and bytes and from bytes as bytes, which is what we did. So
Sorry, what was that?
So I believe you mentioned like things like structures that where you have getter setters for all the fields, right? So you do pseudo initialization. So instead of doing that, we use the init, right? Like from the pin init crate, right? It doesn't need to be pinned, just need to be initialized in place, and so we use that, and we can avoid this kind of stuff. So thanks to that, we can get to something decent using ByGen, but it's not perfect. But overall, I think it's less work than relying on a new tool.
Yeah, and I want to add that I should mentally let's reduce the cost of that, because it's already queued up as a small project, and the firmware team is standing by to do it. It's just not a problem. In fact, the approximate plan is to generate this Rust and get that submitted and all that, and then even follow through with I think we said we were going to actually provide the tool that generates it, something along those lines, or at least the ID. Was it the IDL? Something so that you could trace it back and say, okay, here's where it came from, and post that as like in the where we post open GPU documentation, RefMas. We can put it up there so that people can see exactly how it was done. So that's kind of the plan.
We did something similar for IDLE, the Android interface description language. We both generate C++ and we generate Rust and also Java, and generating the languages directly works well.
Okay.
Can recommend.
I see a question on the chat from Gary. I'm gonna read it. Given that GSP isn't part of a kernel that we need to FFI with, I don't see why we need to describe the info assist structs and use ByGen. Regarding
that's already been covered by David, I think. So.
Oh my gosh,
I
have I been sleeping or what?
Yeah, and I guess just for a little bit of background on what John referenced, RDL, it's an internal description language of these interfaces, and that's kind of where the OpenRM headers, I believe, come from already. So we already have tools to generate .h files, C headers for them. So it's very obvious that you just add the tool to generate it in Rust and whatnot, which is I did look at the obvious way forward really. And if we can, I didn't know we could share that, but if we can share that publicly, that'd be better.
Yeah, I mean, I'm sure we can share the IDL, and I don't know about the tool itself, but
once you've got the IDL, why can't you share the tool really?
I would think so. I would expect that to
the
be
The IDL has all the information that I guess we would care about more.
Yeah, I don't see any issues.
So I'm going to go back to the user mode queues a bit. And years ago, I saw people complain about the drivers not supporting.
Could you speak up just a touch? Louder?
So a few years ago, I saw people complaining about NVIDIA drivers not being able to do implicit sync. And it seems the reason is like we have user mode queues instead of kernel. And implicit sync essentially needs the kernel to track which buffer is a submission accessed. User mode queue bypass that and map them. So maybe this is a question for David, but is the solution still to fix user space, or do we have anything there now?
So the NVIDIA OpenRM stack still doesn't do any except explicit sync, but I think everyone else has realized that we need both. You have to be able to handle implicit sync sometimes. There's just enough interaction points between pieces of the graphics stack on positors and your thing, and you've got video decoders and you've got video encoders, and some of them don't support things. You probably do need default to explicit sync, but you need to support implicit sync. And yeah, that isn't one of the reasons user-based command switching gets to have knowing which buffers are fenced and which ones aren't. But I think that was also something that's mostly been solved by the latest stuff. But the AMD stuff that they've been doing has had the similar problem. But yeah, I think for Nova, definitely we're not going to stick with explicit sync only because I think we realized that, yeah, it's what you want, but there's enough use cases where you can't have it. So I think the last one we saw was problems with was like video encoding on your compositor because you were doing the video encoding with it didn't have explicit sync support. You know. Yeah, if you dot support, yeah. So there's just enough like cases where there's something in a pipeline that you just doesn't have it, and then you need to. You shouldn't need to do it. But yeah, I need to find the reference. But yeah, a couple of people read have a good idea. The compositor team that are like, yeah, look, this is a lot. We've had a lot of meetings. Why we can't get away with the NVIDIA GPU driver? Why there's still problems with Wayland? And it's not. It's because there's always these little cases where it's just like, yeah, that should, but no, there's the next thing in the pipe just didn't support it. Yeah, so I'll dig it up later. And I'll let you know exactly what it was. I have it in my email somewhere. But.
Other questions on this, so we can kind of slide into the user space API, perhaps. Yeah, and if you think of anything about just any questions on this, just bring it up, and we can board these topics. It's not a problem. Okay, so on the user space API, I'm not really sure there's that much to talk about. I just wanted to mention a couple of things to kind of kick this off. Actually, yeah, it's actually good that we have this this diagram on the screen. So okay, great. We've got this kernel mode stack, but now we've got all these user space drivers that are going to use it. And so early on, like a couple of years ago, we used to worry a lot about okay, CUDA is going to need API calls. Are those going to be significantly different than the API calls that OpenCL needs and that Vulkan needs and that even OpenGL, you know, whatever it is that the upstream systems are using? What if CUDA needs something new and special? And so we said, well, the answer to that years ago was, okay, well, we'll just make sure we fortify OpenCL appropriately so that it also has, you know, whatever capability it might be missing. But lately, what I'm hearing is subtleties in that, where it's more like, first of all, I think that a surprisingly large amount of those API calls are shared. Everybody has to allocate video memory. Everybody has to allocate channels. And so you can get a really long ways. Just if you've got a working graphics stack, you know, most of CUDA or OpenCL is mostly working. And we've been exploring that specifically by listing out the API calls typical programs will make and starting to learn that mostly is the case. Second, I've personally been learning that the Vulkan API is nicely very low level and very detailed, so that Vulkan Compute is. Dave was in fact telling me that Rustical, which is an OpenCL variant, is the popular kid today. Rustical could actually be built in terms of or sitting on top of Vulkan Compute. Did I get that right?
Yeah, modular, a couple of features that you need, but they could be added.
Yeah, so I'm a lot less nervous than I was before hearing these latest things, and there's definitely some specific advanced things that CUDA in particular does. One of them is what they call MPS, which is multiple process server or something, where you fire up a bunch of processes, and each one is an SGI style way of thinking, I guess. Each one gets a slice of virtual address space. And the various parts of the driver stack figure this out, and so you can slice up work and hand them out to different processes, and they all coordinate. So it's kind of like one large process conceptually. That requires a few extra API calls to set things up. That sort of thing, that's an example of a compute-specific API. Maybe we end up having to fortify Rustical or Vulkan Compute with that capability. It's kind of right there is the short list of what I have in my mind. I'm sure there's a few other little goodies here and there. So we'll just kind of explore that as we go. But I don't have as many things as I thought I would have to worry about yet. I expect that what's going to happen this year, like Alex said, is we're going to move forward on, we'll light up VFIO and vGPU. In parallel, we'll see graphics and compute start to come up, and we'll just see what's missing and negotiate from there. So,
yeah, like even this week, there's like a new NVIDIA Vulkan extension for like compute occupancy that's been just added. Like it's NVIDIA extension for like I bet you just hit some controls in the driver, but it's like even parts of NVIDIA are doing Vulkan extensions that are probably filling in gaps that we will eventually need anyway. So it's like there are also people in NVIDIA defining some of this stuff for themselves, because I think the Vulkan group are kind of trying to catch CUDA in certain ways. Like they're trying to get equalization with certain like machine learning tasks and stuff. So I think there is a bit of a convergence even happening that we're not even seeing. So it may be worth also synchronizing with your internal Vulkan group.
yeah, it's hilarious. We're now so large that the CUDA folks that I work with, that I've worked with forever, I'm going to go back to them and tell them, hey, by the way, Vulkan Compute is further along than last time we spoke, because last time we spoke, they loosely know what's going on. The feeling was OpenCL was the main one to follow, and now we're hearing that Vulkan Compute is the one that people are piling onto.
Yeah, I think it's Jeff in the Vulkan team is that's been adding this stuff.
You work with James Jones?
Yeah, he's not that team. He's in another.
Okay.
On the Windows side, as far I don't think he uses Linux or Windows. He's just a Vulkan
Sounds
guy.
familiar. I can think of a couple. There's Jeff Layton. There's Jeff. Okay, I'll find.
I'll dig it up as well.
Yeah, I don't really have anything else. So at this point, we just toss the floor open to lingering questions, whatever you got. Otherwise,
I think we worked at some point, but maybe not yet, in listing some sort of requirements on the UAPI. In that, so we have the Nouveau one where we are now, but it has issues.
Sorry, we have the what?
We have Nouveau's UAPIs, like a rough starting point, but we don't need it. Like the legacy stuff is easy to throw away, but there's also. So one of the problems we have currently is and I don't even know if this is fixed on OpenRM. I think it is, but if you run Vulkan info on a laptop which has an Intel and NVIDIA card, and even NVIDIA card's asleep, and it takes 3 to 4 seconds to wake up the NVIDIA card from total sleep. Vulkan, yeah, well, it has to do a full GSP boot in Vulkan, but Vulkan info sits there going, "Yep, I'm good." And for 4 seconds, all you want to know is what card are you? Like all you want to know is like, and you already know that information, but it's just not being cached somewhere, or it's just not. It wakes up GSP. My Nouveau definitely does this. I've talked to, he said it's but it's like those sort of things. Like, when opening the device, currently we always try to create a channel. Like, is that something we should not be doing? We should probably open the device and not be creating a channel, because creating a channel wakes up GSP, and it's like so those sort of like some of those semantics around what we actually do in each sort of stage of opening space, and because.
I guess we can be a little bit more flexible with respect to say when we do operations. Right? I think OpenRM is very lazy. It loads the GSP at the last second and so on. So right now in Nova, we are loading it at prop time, but maybe it has issues with suspend resume as well. So
yeah, we're super lazy, right? Like you load the driver and it does nothing basically for OpenRM until you try and open it, and then it takes forever, potentially, well, not forever, but like sometimes seconds, minutes, even memory to open that, because we have to initialize the GPU, initialize memory, and then you close that again and that gets all turned down. And guess what happens when you open it again next time? And so we have all these weird workarounds for that. So I think it's a valid point.
Yeah, we
have to
ways of keeping it open.
Figure out what we want to do at probe time, figure out what we want to do at open time, and suspend resume.
So what's the to speak like a Rust developer? What's the idiomatic way of doing things nowadays upstream?
Yeah, like not that way, but yeah, generally all the DRM drivers follow the same pattern of like at least the like on load, you initialize everything, because we generally want the display to come up. So we don't do lazy on that sense. That on open we'll do, but on open we all make the mistake of talking to the hardware or trying to create channels. And I think that's where we have to start setting, because GSP takes 3 to 4 seconds, but it's very noticeable when you have to wake it up and just to create a channel, just to tear it all down again. Like, it's not doing. It's because it's runtime suspended, not because it's
been because you've torn it all down. It's because
Yeah.
the GPU has been put to sleep by the system, and then you wake it back up again, and that involves.
So it sounds like what we're saying is that we want Nova to do what we internally call init on probe, where
we would init on
probe. You initialize all the GPUs, right?
But then from user space, whether opening the device should wake it up, we should try and avoid that. Like that's one of the it runs into
don't necessarily wake up the device when the file is opened.
One of the fun things with runtime power management in Linux is the best way to describe it is like when you realize you needed to wake up the device, it's generally too late to wake up the device. So the best time to wake up the device is the very first time you enter the kernel. Anytime after that you've taken a lock and then you have to wake up the device, you're going to hit a deadlock somewhere because generally you're 4 locks down when you suddenly go, I need to talk to the hardware and the hardware's asleep, and then you hit the PM runtime bit and it's like, okay, now I need to use all those locks you just locked and I don't have anything to tell you. So we generally try to do the PM runtime wake up on the ioctl handler, but I think we could design things a bit better for this process that we would still take it early on certain things, but maybe not on open, or maybe not on the ioctls that just do information we could cache. We should probably cache a bunch of information at the first time and create a channel so we don't have to keep generating it every time, and so that we can get at least through like the Vulkan info or the like starting up an application that's not ours.
Right, but when do you wake it up?
When you're probably setting up a VM or channel, like the first, you could do a channel allocation ioctl or a VM allocation ioctl. Like currently that's all implicit in
so
open.
Like first channel allocation or something?
Yeah, like we implicitly do all of that in open on Nouveau, but I think we should try to figure out whether we should separate that out into a separate ioctl for alloc channel and VM or
okay.
That's we should be wary of just copying Nouveau because we know there's definite mistakes and or I wouldn't say mistakes, but things that have been later came to be problematic.
I'm trying to reconcile that mentally with the init on probe idea. Oh, okay.
I think you're sort of talking about caching some of the information, right? So that, when you resume from suspend, you don't have to open the hardware to figure out what GPU you're talking to. It's just cached there already because you would talk to it before you suspended the device, right? So, and it's about figuring out what information we can or should cache, I guess. And then at what point do we go, well, now we actually want to do something with the GPU.
Oh, okay. So I'm hearing we still do the init on probe.
Right.
Wake up all the GPUs on PCI probe, and then the driver caches information about them so that when you resume, you don't necessarily have to even call open. Is that?
Well, you call open, but you don't have
open?
You don't have to go and wake up the hardware to get the information. I don't understand fully
so you
what
call open, but
information
you don't have to
happens,
hit the
but-
hardware to get the basic information.
Right. That's, I think, what Dave's describing.
Because right now, if you use Vulkan as the backend for GTK and you start a GTK application, the first thing it does is probe every Vulkan driver in the system. And as part of the probe of the Vulkan driver, it has to enumerate the device and get a bunch of information about it. And if the kernel, if you can minimize, and that has to open the device, it generally asks a couple of get information questions. But if the first thing it does is the device does when you open it is create a channel, and then you have to talk to GSP, you're instantly, every time a GTK app, even if it's just going to run on the Intel side, it still wakes up the NVIDIA side, and there's just no need to be waking it up at all for that sort of stuff.
So how much of this stuff already exists in other drivers? Or are we just paving the way here?
This will be that. I think we've hacked, because generally these are ABI decisions that were made 15 years ago before we had runtime suspend. So we didn't do the right thing, but we should start from the point of we know this is a problem now. And we should make sure we do our best to not cause it, to keep it going. So.
Yeah, on the OpenRM, there's a belated understanding that init on probe is desirable as well, actually.
Yeah, and I think there's been some discussion about that, because if every application starting hits the GSP lock, you end up serializing a whole load of stuff because everyone then wants to send a message to GSP to just get the information about the driver in the system. So if you have a bunch of Vulkan applications starting at once and all they're doing is saying, is what driver's in the system? I want to pick one, and it doesn't pick the NVIDIA one. You still end up serializing them all because they all have to go through the GSP lock, which is a single thread.
Are we out of topic and questions already, or is there more? Yeah.
Coffee break, sorry. Yeah.
Okay.
Yeah, well, so I guess it's a good time for coffee break.
I would not want to.
People will talk and then they'll have topics.
Parser. Every single way for
Sounds a lot easier to get across directly. You don't get a lot nicer.
I knew it was horrible. So what we were originally doing, I was like, that's as far away. Yeah,
I don't think you can. My favorite, I think. Yeah. Oh, I can't talk about how. Okay, I'm not. Right. I managed to get some Indian. I don't make sense.
Most of the way through.
Oh, that's right.
Not to change direction. You have no time to change direction. That's a waste of time. Okay? I don't like getting stuff and dropping it into. So, also we have.
that's
Right, like, it just works by area. Yeah. And that's what we do. No one else. At least they've already tried. Exactly.
Are there any disadvantages? Once you attach it, I didn't mind what the whole obviously, easier attachment is. Yeah.
I'll think about it. You want to give it right?
I will not say that. Otherwise, you will. Otherwise, everyone will say someone. Say that guy.
But you'll say afterwards.
Okay. When you said, oh, I binary was easier, I mean, we always. I have the idea already. I will have one direction for it, and it's very easy to separate.
Yes, yes. I was looking at
My gen is just by itself. Okay, then in the above you have to tell. Find the people. Well, nice to have you.
Yeah, yeah.
If you're around later,
I am.
I wouldn't say I engage.
Yeah.
I think
Maybe last week.
yeah. Did you get gifts from? Because I was going to ask if Alexander is going to get one.
Oh, yeah.
Because he was a speaker in the
Right,
I
yeah.
am asking who should we give it to? And if the people I'm asking say, oh, Alexander is a candidate, but if he's getting one, then I can give it. Okay. That's why I was asking.
So I don't know. Yeah.
Okay.
Yeah. Yeah, you're gonna see, we spent the last year ramping up. Now we've got, a ton of. And so I think this year, we're gonna see pretty fast, plus we're gonna check.
Yeah, I think we're yeah.
So this.
That's
kind of. So, yeah, that's
what kind of people told me.
Yeah.
And also somebody from media manager. I don't know where it is.
Yeah.
Okay, yeah. Somebody told me that, you can go to Microsoft because the Microsoft were being hit. But since the optimistic ones, so they are like, oh, if we could hit the fuel next or whatever, we would actually be able to work on it. They would give us the So apparently that's good news. Okay.
Yeah, I guess that's good news. Yeah, the main barrier is, of course, last training, but you know, we've got a year or two or more to get that to happen. So, and I just adopted another manager. Now that one that I'm calling you.
Yeah, I didn't mean to. Not too
Now I
bad.
can attach people to him. Oh, you work for me, and he can start helping me go, okay, and you need to start training less, and, you know, and we can just start. It's fine, 6 to 12 months to really get comfortable.
You have to spend more people there already. Although if you generate most of your stuff and you don't need to, then we will be on the game.
Yeah, the findings is gone. That's going to be fun.
But you have the still findings.
The more time passes,
the easier I think you will get. Easier, the more time passes, the more Rust will be in the kernel, the more native Rust interface will be in the kernel, and the more you will be able to do. There was another idea. Again, I don't know exactly what it is. I have to be my boss. It was not a kernel. They told me, no, because where do I find the kernel? I cannot find the people I need in my department. Well, I don't think it was good. They were like, what is it? Because I need people, right? What do I find it? Exactly. I told him like, it's slowly, there, bring the other stuff, try to build things, working together and so forth. People kept asking, like, I think we're making it up like maybe solution one. Like,
Yeah, here you go. Actually, we got the 20 people in the back, you know.
Hire them.
Really?
Yeah, give them money.
That's right, that's right.
So I could.
Yeah, it's hilarious. Okay, I need.
Yeah.
Oh, and Colonel. Oh, okay, now we're down to 3 people. And Russ. Oh, what? It's kind of quiet around here. You guys.
So I'm trying to also help. I mean, not the media. You have money and you know. But what I'm trying to do for someone
I say that word.
Yeah, sure. So what I have been trying to do on this trying to see this thing. They another company, smaller company.
Yeah, about that. Yeah. So Rayos, he said, oh, you guys see backlogs over the law. So it isn't like a law that says
okay, so what I asked is, I asked to see just we don't pay.
I can easily do that.
So that's what the only thing I asked. Yeah. In some companies, of course, you have to go. Even in big companies. So but it was, what I mean, that is was to support the freedom. Again, I get things done in the kernel. This is the other action. The experiment thing, now is an experiment. That's the intention, or at least. I don't care.
We did experiments over, piling on.
Actually, Google told me yesterday because I asked them because John was asking for that. And I was like, oh, let me ask them. Actually, they checked the list. That's what they didn't know. Yeah, there is I said in the talk, in the calling matter, no, you have to call matter. Today, there are millions of devices out there. With last name, with the Aspen. What I was saying to you is, I hope that at the end of the sprint, signals all the companies that are like waiting, take risks. Some of their employees also can like, yeah, I want to be Rust. It's a good moment. You're one consultant, right? We're going to account. So you need to be Rust, but there's going to be
I just need to figure out where to put the words.
Yeah, and I can send you the link of the page, and you see there is Google, Microsoft. just want to have you guys, because then I can put you the logo in the cost. I mean, it was a win-win. Excel companies always win. For you, so you appear on some possibility that invested for for us, it was easy. I mean, now the experiment is over. We don't really need it anymore, but I am fine putting you guys. I don't know where it's like,
Because I can get the little stamp real quick.
Yeah, but I was trying to, every I can say, of course, in your case, I feel very safe because you have to be working in public, so it didn't matter, right? But for example, there were Microsoft gave me a statement, and they were not really, but they gave me a statement saying, wait, right, and saying, well, we have something, I don't know how it works, and we want it to happen, right? They said, we want it to happen because we want to use it for something without they were not working. And without the statement, I have to say, hey, Microsoft actually either they are working with this or they want to use it.
Right.
And I know internally they told me they were using it.
And we went the opposite approach, people and all that would be uncomfortable.
Yeah.
So, and the patches speak louder than words, so we just started doing
that's
it.
my truth. I mean, if
So
every
it
company
worked
put
out.
5 engineers on the thing, then it would be over years
Right,
ago, right?
yeah.
So, no worries. I mean, I didn't mean to press on it's not C approach me in or I approach and we talk, and I was like, hey, well, media sending people to the rest as well. I mean, you have like 5 people working full time or whatever. So just I thought it was like something that you like.
Well, what happened was a little bit lost in translation.
Oh, no worries, no worries.
I thought you were looking for.
No. It's just really.
Yeah, we got it.
Here we have. I just wanted. I don't exactly know what they are doing, but they said, no, yes, I will want to do that statement. They didn't actually ask. They were. I don't want to put you guys there.
I can definitely write up something and get it.
Yeah, I mean, it's not right. There's no like. I know. I mean, I just need to convince Linus anymore or the other. Really, so I think it's not very good.
Had a list of, well, this might not happen, this might go around.
Was a bit off I think somebody told me you were the one that avoided internally.
Yeah. What happened was like. Before that, and also report that went on for a year. And then I was kind of looking at this. And I was okay, you know, I would do something, but I had really command. Happy not to be leaving because it was going nowhere.
So I think that has come to. I think it's Linux. I think it's Linux. For me, way better than how it goes. My opinion, better than Angular.
Yeah, file system, we always have this rule. Better to bug on and panic the moment you detect error. So you don't want to continue. We've been panicking.
Yeah, also,
Not a file system.
Fix it, right? But the thing is, don't do it. Like, stop doing it. I go on because you know why you are even testing. So, but the thing is,
the other part of that reasoning is bug on, make sure.
Exactly.
So it's a lesson learned over time.
That's
nice. Then we learned that start debugging in the
yes, but that's for. Funny. You lose the thing. They use it. Second thing, they don't ever want that data correction continue. Anybody reaches that, they want to stop the server. That is what happened. In case somebody was trying to exploit it, right? And then try to then it was exploited. There's two kinds of
and you don't want the data.
Exactly. It's like, to hit that order was our issue, right? A memory error, but it's two kinds of user. You cannot reconcile both, right? There's two kinds of user, right? My opinion, there is a middle ground. Yeah.
Bug-ons.
That's also.
All right.
I know that they get it, but
that argument's wrong and dead. Write the warn-ons. If someone wants to panic, because we have all, we are in the process.
Better than the bug on, according to
Don't think that these are going to.
Greg, have a little word on, which is
not in file system.
Okay, yeah.
He's the number two guy.
There is a second thing with the, right, which is burn on continuously. Or you have the problem of trust, equivalent would be unsafe. You're not really gaining anything. You cannot really do a warn on. Don't gain much because
warn on returns value.
We can do
back
that.
Up the stat.
We can do the warn on, but then you have to handle that, and therefore
you have to move it back up.
For something that you know will happen, right? So we are back into the returning something that cannot even happen. That's because it's impossible.
Line of reasoning is the other line of reasoning is that The old concept, which is, I assert that this cannot be true. What do you do on?
Oh, what they are saying.
Don't have a
Don't-
search.
don't-
They're saying,
don't-
they're saying
Exactly, don't do it.
which goes somewhat.
Yeah, but that's what. So when you are a cloud provider, you can do that. They are also thinking about the user. That's the thing. Like there is cases where there is no.
No higher level,
There is no reset mechanism.
Right, but I mean, think about your alternative.
Well, that's what Danilo is saying. Well, I failed the system. Oh, that's it.
I mean, supposedly, you got this because it can't help. So, I mean,
But
that's
then-
where the argument falls
yes,
apart.
Yeah, but the thing is, even you would say, no, that's fine, right?
It happens, so why worry, right?
My argument is. Also, we cannot catch back because.
I guess you could do it.
Yeah, that's what we request. Hey, let's have a thermal. Where we have a
warning
plan, like we have that, like that. That's powerful, right?
I'm just, you know, at a higher level, I'm worried about the form of reasoning that goes absolute. Stand back and look at it.
From
Wait a
my
minute.
point of view,
That's
what I
not
do is
quite where I wanted to
it's a
end up.
middle ground, you know.
Exactly.
And it depends on the case.
Yeah,
Depends on the
let
case.
what
Depends
they
on
need.
the subsystems. Same
Depends on the environment.
Exactly, exactly. So,
Yeah.
but
So
I'm
you have
trying
to
to
be
see
really wary
where we
of
are,
these
and that's why I
absolute-
said, you remember. Where is the?
I was pushing, I was pushing for, let's balance away.
One of those middle grounds, because it means that at least we get the developers to really think about it. And they don't have to have a grab from. But I'm trying to
But I
avoid
don't
is-
want slash.
No, I mean, it depends on what we, depends on what we,
That's my sense of.
depends on where we want to put it. I was talking about Angular. The other- I was not thinking of the operator. Well, if this is unwrapped, I mean, I agree that we don't have. Like, most of the time, there is a better way to write it. The thing is, what we want to support that somebody just use Unwrap because they are lazy, they allow Unwrap. If they have to write a comment, then it's more painful. And therefore, if they write it, they have to think about, oh, could they avoid, can I do it another way?
I
right?
kind of get that. I'm also wary of the. They make it really
No, they make it
impossible
to
to drive.
drive.
Yeah.
Or
So
be
then they
expensive.
won't drive. So what happens is people. Now they're.
Yeah.
Questions about this. So we'll end up- you don't want to write such and such. You have to anyway, but. I'm not really arguing.
I have to say, no, I have to
Cautionary
say,
thoughts.
I am asking, my role kind of. Where we end up? Is it exactly where we end up? 3 or 4 sides of the airplane.
Yeah.
Okay.
Yeah.
I'm trying to see, okay.
And as long as we're talking about this area, I mentioned. Unhappy with. It starts off with.
You are currently the only person in this conference.